Okay, hit the record button and we start. Okay, so preamble done. Let's cut straight to the chase. Tonight's talk is well, welcome to London. You see, that's my window, my skyline kind of background out there. And yeah, welcome to London. And basically, it's cold here. It's really cold. So tonight's talk, okay, straight to the chase. Tonight's talk is about artificial intelligence and machine learning. We are basically going to tackle practically every single major issue in artificial intelligence and machine learning today. I'll do a screen share, and these are the issues. And we're going to systematically go through all these issues, and these are really kind of, these are practically all the issues, major ones in artificial intelligence, machine learning. Okay, one, we'll show that the answer to these problems and issues comes directly from neuroscience. Okay, so it's grounded in actual, like empirical evidence, grounded in science, basically. And secondly, we show that when we put all these kind of solutions to these pieces of the jigsaw puzzle together, we then see a very clear, crystal clear path to the creation of true artificial intelligence. So, okay, this is like the talk 2 weeks ago. It's going to deal with a huge subject matter. And like I did 2 weeks ago, we're going to basically bring some clarity to the issues, I believe. So there's this thing called artificial intelligence. Okay, there's a trouble with artificial intelligence in the world today. There's all this hype about artificial intelligence, but the problem is there is no artificial intelligence. We have technology from 40, 50 years ago kind of hyped as kind of like cutting edge breakthroughs, but really it's not really doing the job, and we have like artificial stupidity, really. What we're going to do tonight, is basically show a really path that's grounded in science and neuroscience, and show how to actually create true artificial intelligence in very soon. I mean, we want to do this ASAP, basically. So, by the end of this talk tonight, you're going to see that true artificial intelligence is going to come sooner rather than later. Okay, so these issues. Okay, so a lot of these issues are resolved by latest findings from neuroscience, and these findings have literally only emerged in the past 5-10 years. We're going to start, just go straight to where a lot of the action's going on, and it's to do with neurons. It's how neurons work. So existing AI machine learning is based on a model of the neuron that is essentially about 60, 70, almost 70 years old. McCulloch-Pitts is kind of an old idea of the neuron. A lot of neuroscience has taken place in the past 60, 70 years, but the existing artificial intelligence, machine learning neural networks is still based on this very old model. In the next 10, 15 minutes, I'm going to totally blow away that existing model that's still used in mainstream artificial intelligence and machine learning research. Okay, so cut straight to the chase. A lot of the exciting new research is to do with neurons. Okay, so let's talk about the beginning of the talk, first section. Let's update our knowledge of how neurons actually work, real neurons in real brains. Okay, firstly, neurons, are dynamic. Okay, these artificial neural networks, they're static. Basically, you got the nodes, you've got the connections, and they're static. And then basically the learning is over these static weights, static synapses over these static neurons. But real neurons, they're actually very dynamic. Now, this is an animation. This is actually real neurons in a petri dish, and they move about. They send axons, exploring dendrites always grow. And it was thought that basically this was a kind of like something, only newborn babies, or kind of like something that happened a lot in kind of like, young animals and stuff. But this process actually goes on in most of our brain. So basically, the brain is constantly, in a sense, reconfiguring. Now, okay, in that animation, okay, the neurons are exploring very fast because they're in a petri dish, and it's speeded up. Now in the brain, okay, most of the brain, these main, what's called pyramidal neurons in the cerebral cortex. Now the movement in the brain, because it's very tightly packed of all these fibers and lots of hundreds of billions of neurons and stuff, but they still move. These axons, these dendrites, they still grow inside the adult brain. Now the movement in the adult brain is glacial. You can hardly see it. I mean, it's less than 1 millimeter a day. But in aggregate, there's lots of movements because there's billions of neurons and trillions of these dendrites, but they're constantly in motion. That's the thing. Okay, so the actual physical dendrites, I'll show you a picture of a neuron here, the actual physical dendrites and physical axons are constantly in motion. Not just that, but what's on the axons are what's called axonal boutons, which actually form the synapses, and what's on the dendrites, the receiving end, is we've got these kind of, like synaptic spines. And on top of the physical growing of the dendrites and axons, these spines and boutons, they constantly move around much faster than actual growth of the dendrites and axons. So you see, a real neural network in the brain is dynamic. It's constantly reforming, constantly. And in aggregate, even in a second, in a minute, there's constant reconfiguration. In aggregate, there's lots and lots of reforming going on, even in a moment, in a minute, in a second. Obviously, over several days, several months, it reconfigures a lot. Okay. Now, okay, so neurons are dynamic, and on extreme end, it was thought that new neurons didn't form, but that was blown away. That idea about actually a few decades ago now, that in the dentate gyrus of the hippocampus, new neurons, completely new neurons form in adult brain. And we're not talking one or two, we're talking thousands every day in a very critical part of the brain to do with memory. And of course, these new neurons will then grow out dendrites and axons. Okay, so dynamic neural networks in the brain. Now, a very exciting finding is this idea of dendritic patches. Let me give you some context to explain what it means. Okay, so that's basically your brain. Okay, that's a kind of diagram of your brain. Okay, so that's your cerebral cortex. Okay, that's kind of like a sideward view. Now, the cerebral cortex is actually a flat sheet. It's literally flat. It's a lamina. It's like a sheet. If you flatten it out, on two sides of your brain are these kind of like handkerchief-sized sheets, about 2 millimeters to 2.5 millimeters thick. And the entire cortex is made out of a basic building block called a cortical column. Now here we have a whole bunch of cortical columns arranged in this kind of like a tessellating pattern, and basically your entire cerebral cortex is made of these cortical columns, which are about 0.3 millimeters in diameter and about 2 millimeters in length. So, okay, we have a selection of neurons that are found in a cortical column. So in the cortical column, a microcolumn has about 100 neurons, a macrocolumn about 1,000 neurons. Okay, so we're talking about 1,000 neurons in a kind of like standard cortical column. Now, these are inhibitory neurons, about 20%. Now, these pyramidal neurons are the main workhorse neuron of the human brain, because most of your brain is cerebral cortex. Now these are pyramidal neurons, and a blow-up of a pyramidal neuron is what we saw earlier. So here is a pyramidal neuron, and that's your main workhorse neuron of your brain. Okay. So the exciting new finding, okay, is that basically it works in a completely compartmentalized way. This is completely new. It blows away existing ideas and approaches to artificial neural networks, machine learning, and artificial intelligence. They work in little modules, and these little modules are literally kind of 20 to 30 micrometers across. Okay, now if that pyramidal neuron, that's about less than 2 millimeters, maybe kind of 1.5, 2 millimeters from top to bottom. Okay, then what we're talking about when we talk about like 20, 30 micrometers, we're talking, look, see me shape my cursor, we're talking about tiny little slivers, like dendritic patches, compartments. And each of these compartments, they process information separately from all the other compartments. Okay, so what are these compartments doing? It's really fascinating. They're doing something quite fascinating, because these compartments, 20 to 30 micrometers across, they are basically taking inputs from different neurons, okay? And basically they are conjugating. They're basically detecting correlation, and they're binding inputs from different neurons. Now, these clusters, they tend to correlate these signals from different neurons, and then these clusters tend to be stable. And if these clusters don't take inputs from different neurons, and they die off and have to reform to form new connections between other neurons. Okay, so basically it's like a building block. It's like a building block of conjugation. You're literally taking different inputs from neurons all over the place. I mean, maybe on the other side of the brain. And you're forming these little modules about 20 to 30 micrometers across, tiny little segments on this huge well, relative to 20, 30 micrometers, we have literally there'll be tens of thousands of these little modules on this pyramidal neuron, you see. Now, okay, so what it's doing is, yes, it's kind of conjugating across these little patches. So, okay, so we have these exciting dendritic patches, compartments doing this kind of like, like learning across a tiny little patch. Now, another new finding is what's called dendritic spikes. Now, the old model was basically had a neuron and the cell body spiked, and then the action potential, and then the signal transmitted down the axon. What's discovered now, okay, is that all over the pyramidal neuron, all over the dendrites, you can have localized dendritic spikes. And these dendritic spikes will travel towards the cell body, but they're localized. And also, we'll talk about in a minute, they also do a backward action potential. And critically, these local dendritic spikes that can happen all over the dendritic tree, they can support what's called long-term potentiation, what's called spike time dependent plasticity. What this means is that these local spikes working with these local modules, patches, creates kind of autonomous processing cells along the dendrite. We're talking not thousands, we're talking tens of thousands of these autonomous processing units all across a single neuron. It blows your mind, doesn't it? Okay, it really does. It's really complex, and a simple neuron has lots of computing power. Now, these dendritic spikes, okay, it's also found that the main dendritic branch from the cell body, each of these main dendritic branches have a separate spiking zone. So from the cell body, the soma, you have the main branches. Each of these have separately a spiking zone, and each of these spiking zones can separately activate the entire neuron, you see. So it's basically like disjunction, like that main branch or that main branch or that main branch can actually fire the entire neuron. So that's like OR, logical OR. If the what we saw earlier across patches was like conjunction, you're basically correlating, you're ANDing basically. This is like a logical OR. Okay. Now, okay, so dendritic spikes really, really important because it modularizes basically what was thought to only occur in the cell body, but it's happening all over the dendrite, the input tree of the neuron. Now, the next very exciting finding is what's called backward action potentials. So, okay, it's been known for a long time, okay, for 30, 40 years that a main neuron called the Purkinje cell in the cerebellum had backward spikes that went from the cell body right back to the dendrites. In the past, kind of, I guess, 10, 20 years, it's been found also to occur in the other main processing types of neuron, which is the spiny stellate in the striatum or basal ganglia, the medium spiny stellate, but also critically in the pyramidal neurons of the cerebral cortex. So it means that when a neuron fires, then you have a backward action potential that travels backwards, not down the axon, which is the forward transmitting path. It travels back along the input pathway, the dendrites. Okay, so it travels backwards. Now, critically, the localized dendritic spikes, all over the dendrite also produce this backward action potential. You see, it's like fractal. So the entire neuron does it, but also little patches of dendrite also do this backward spike. Okay, so what's really interesting is basically this backward action potential going backwards then interacts with the forward dendritic spikes. So there's a kind of interaction going on. Okay, they actually mutually reinforce one another. So the backward spike can actually prime or make more likely the dendritic spike, but vice versa, the dendritic spike will prime the backward signal. Do you see what's going on? There's a kind of forward-backward association going on between the cell body and the dendrites, and it's happening in a fractal way along an entire dendritic tree. It's kind of forward. I send you a forward signal forward, and kind of then you have a feedback signal, and they kind of reinforce one another to the point where a backward action potential can prime a dendritic spike. Then you have this kind of positive feedback cycle which pushes what's called the pyramidal neuron into burst firing, and that really is firing like crazy now. So it's like a mutually reinforcing cycle. Okay, so that's very exciting because it's basically showing that the input and the output, basically, there's a mutual kind of like association going on. There's an association mechanism going on, not just between synapses across a dendritic patch, but across the entire tree, basically, to the cell body, a kind of backward-forward chain. Now, the backward chaining aspect, point 5, okay, this is like 30 years ago, I read an article, a science paper. I was still in school, actually, in Scientific American magazine. This is the first example of backward chaining that I learned about. And it was basically there's the CA1 neurons in the rabbit hippocampus. And what they found was, as training progressed over days, over weeks, there was a backward chaining of this chemical called protein kinase C, which is critically involved in memory formation from the cell body back along the dendrites as training in the rabbit progressed. And new research has shown basically that there really is this kind of backward chaining process. Now, when dendrites grow, okay, that when they physically grow backwards, okay, what you need is a branch to be stabilized by synapses. Okay, so you need those patches again to stabilize, to cross-correlate, to stabilize that branch. And once that branch is stabilized, then it sends back, it grows backwards. The dendrite grows backwards. It's like a backward chaining of growing of dendrites. And there's a complementary a kind of like signal whereby, okay, once the dendrite is grown, okay, you have these backward action potentials. Okay, if the backward action potential that's primed by the dendritic spiking, this kind of mutual toing and froing feedback forward, kind of mutual interaction we talked about earlier. Now, if the signal doesn't get to the distal, the more distant dendrites, then what happens is it long-term depresses. Do you see? So it's correlating the signal, saying, yes, there's a signal there, so therefore I associate. But if the signal doesn't arrive anymore, then you prune it away, you see. So it's like a backward chain, but selective. It's actually associating according to the signal of the main cell body. So it's like an incremental growth process. Okay, I'm going to elaborate on this later because it was really important for how we learn and how neurons learn. Okay, point 6 is that what's discovered now is that the idea of a neuron as a simple linear summation device, okay, that the cell body just sums all the signals going into it, and that's all it does. Well, not anymore. Basically, these modules, dendritic branches, perform all the basic Boolean or logical operations intrinsically within itself. Let me explain. Okay, the XOR operation is basically a fundamental Boolean operation. It means, OR is basically, say there's two branches, okay, A and B. It means branch A can activate the cell OR B, so that's disjunction, that's OR. Okay, now XOR means basically, yes, branch A can activate the cell, branch B can activate the cell, but if they're both active, then exclusive, then the cell is not active. So it's a fundamental Boolean operation. Now, it was believed that basically, one of the shortcomings of the first generation of artificial neural networks couldn't do XOR. And this was seen as a flaw in the first generation of artificial neural networks. Now, based on very simple ideas of how neurons work from 40, 50 years ago, yes, XOR is a real hard problem for these first generation of artificial neural networks to do. But now we know that real neurons can do XOR across a branch. So a tiny branch across a dendrite, a dendritic tree, can do XOR. That was discovered over 10 years ago. What was discovered just literally about 2 years ago. Okay, 2 years ago, this was discovered. A dendrite can do XOR over a tiny sliver of patch. So across literally tens of micrometers again, it can perform the XOR operation. Two synaptic inputs going in, A or B will activate the patch. But if they're both active, then not. See, that's the complexity of neural processing now that's been discovered literally in the past, past few years, past 10 years. And of course, all the other Boolean operations like AND, okay, so, this branch and that signal summates, and then it passes that one and not logic through what's called inhibitory neurons. So it shows basically neurons are now not just simple linear summation devices, they're actually very complex combinatorial processes that even tiny slivers, tiny little patches, tens of micrometers across, can perform these really complex logical operations. Okay, so that's just blown away the old model of neurons. I can go on. I mean, temporal complexity, it's found now that basically even neurons, even on a cell membrane, there's like a dendritic oscillations, and these oscillations will synchronize with the cell body and synchronize across the dendrite, and that will basically influence processing on the dendritic tree. So it's like brain waves. Your entire brain has brain waves, but your neuron has local waves on the dendrites, and they synchronize or desynchronize. That actually affects information processing. Fascinating stuff, isn't it? I mean, but the main thing is it blows away this old idea of neurons. This is basically your biological neuron versus artificial neural network. Okay, so even in new neuroscience textbooks, the idea of neurons is basically just way out of date. And the idea of a neuron used in artificial neural networks, which is this basically, it's basically linear summation into the cell body, some kind of activation function, which is like sigmoid or what's called a rectified linear unit or radial basis function or whatever. Okay, the new idea of neurons just blows away this old conception. Do you see? So okay, that's the kind of like the stepping stone for this new generation of artificial intelligence. Okay, so we're gonna. Okay, that's a good book to read. That this is from 2016. It's basically called Dendrites. Okay, so it collates a lot of information that has been discovered in the past few years. It's probably the standard, most authoritative text on dendritic processing today. So it's worth going through. It's quite a telephone directory of a book, but it's worth having a look at. Okay, now, okay, so we're going to turn our attention to AI now to resolve these issues. Now, immediately in AI machine learning today, okay, according to some of the biggest names like Jeffrey Hinton, like Jürgen Schmidhuber, that today one of the biggest issues is this thing called compositional learning. Okay, so the existing neural networks like XOR from the last generation of neural networks, it's having severe difficulty doing what's called compositional learning. But given our new understanding of how neurons actually work, neurons are fundamentally doing compositional learning at the level of the dendritic patch. It's a non-issue. It's like XOR from 30 years ago, the issue of XOR from actually, God, it's 45 years ago. Okay, it was a non-issue because neurons do XOR intrinsically at their branches, or dendritic branches and dendritic patches. Today, the issue of compositional learning that the existing artificial neural networks are having difficulty doing, and it's basically a major problem. It's intrinsic to how neurons actually work. It's a non-problem. You see, this new generation of artificial neural network will actually just basically, it's how it works. You have this kind of old view of neurons, which basically is out of date. It's based on an idea of neurons which doesn't correspond to how real neurons work. And you're having trouble with compositional learning. Whereas the new understanding is showing us that basically the brain, neurons are inherently compositional learning devices. Okay. I mean, compositional learning is like compositionality is like language. You can composite letters of the alphabet to make words, composite words to make sentences, etc. That's compositional learning, which the existing generation of artificial networks actually has difficulty with. Now, another thing is incremental learning. The existing backpropagation networks, they suffer from what's called the Achilles heel of the existing generation of neural networks, according to some of the leading lights. Jeff Klein of OpenAI, the AI company that Elon Musk started, said it's the Achilles heel of the current generation of machine learning neural networks. Now, catastrophic forgetting basically is this thing where your neural network is taught a new skill, or it's taught to play a new game. Okay, so it's playing one Atari game. You teach it a new Atari game. What happens is you totally forget how to play the original game. Okay, so new learning erases old learning. It's pathetic, isn't it? I mean, basically, obviously, we don't work like that. We don't, learn a new skill and suddenly we forget our old skills. But this is how the existing generation of machine learning, the cutting edge, that's how it works. And this is called the Achilles heel. Now, what we've seen with this kind of like a growing dendritic backward chaining process, inherently, how neurons are learning is incremental. It's an incremental growth process. You see, it's very different from existing models of neural networks, a kind of vector space, and you kind of shift all the vectors to all the neurons. Learning inherently involves this kind of like a compositional incremental process from the backward chaining from the cell body growing outwards. It's a growth process like a tree. Okay. Okay, we're gonna it gets a bit more abstract now. Okay, there is something that neurons are doing, which is very fundamental, and it's basically relates to what's called Lindemeyer systems and diffusion limited aggregates. Now, in the neuron book I showed you earlier, okay, there's one chapter, chapter 17. It's all about how to create mathematically neuron shapes? How do you create, like physically on a computer screen, create a shape of a neuron, nice graphics and stuff? Two things they use is what's called a Lindenmayer system and what's called a diffusion limited aggregate. Let me explain what they are quickly, because they're quite fundamental concepts. Now these are trees, okay, but they don't exist. They're actually computer generated. They don't exist in real life. Okay, they're actually generated by what's called a Lindenmayer system. Now that's with nice colors and pretty graphics. Okay, now here are more kind of abstract looking, austere mathematical trees. Okay, so this is the same thing, but in a kind of more abstract way. And basically, they're generated with this Lindenmayer system. Like that's just a Lindenmayer system. You see, where I'm shaking my cursor, that's all it is. See, it's basically it's like logic. It's what's called a string substitution system. You have the initial variables A, B. Okay, you have the initial axiom, and you have a simple rule. If I see A, I can map it to A or B, or the other rule is if I have B, I can map it to A. Now that mapping is called a string substitution. It just means every time I see an A, I substitute the string with A, B, and if I see a B, I can substitute that string for A. And by substituting the string, you can then create these kind of like like sentences that can then be rendered as tree structures. Okay, so dead easy. Now these string substitution systems, Lindenmayer systems, are part of a bigger family of systems called string substitution systems, and they include things like lambda calculus, but also things like Chomsky's generative grammars, but also logical inference rules. What's called formal axiomatic systems. And now all mathematics reduces to formal axiomatic systems. So this very simple kind of thing that generates trees is actually fundamental. You see, all mathematics effectively reduces to this kind of system. Okay, that sounds wild, doesn't it? But this is this is a fact. This is not speculation. Okay, so that's a Lindenmayer system. It creates trees. Okay, it generates trees, and you use them to generate neural trees. Here's a simple fractal binary tree. Again, a different set of rules, and that's the tree growing step by step by step by step. So that's called a Lindenmayer system. Now, diffusion limited aggregate is basically a fundamental growth modeling process where physicists or complexity scientists use it to model things like growth of cities or growth of algae or growth of snowflakes. You have a central point, okay, and they're basically, the point is sticky. And these points around it, these kind of particles will basically random motion, Brownian motion, zip around it. And when it hits the central sticky point, it sticks onto it, but itself becomes sticky. You see, you recursively do it again and again. Now here is a simulation where, okay, you got 4 colors. Okay, what I'm doing is basically when the particle sticks onto the sticky point, then it, okay, sticks onto it, but it takes that color and then it becomes sticky itself. Now in this animation, we're going to show basically this animation. Okay, that's the entire shape that gets formed. Okay, that's how it begins. You see, it's kind of growing back outwards. And as the black spots, you see it's zipping around, and as it sticks, it kind of grows outwards. Now, these are what used to be called slow grows, because back in the 70s and 80s, when they first discovered diffusion limited aggregates, you run the computer all night and you kind of get halfway to here. But now computers are so fast. I mean, this is a slow simulation from years ago, I wrote years ago. But now, you can fill the entire computer screen in a split second. So they grow very fast now. Well, the basic principle is basically, the stickiness of particles drifting around randomly, sticking, and it grows into this kind of like random tendril-like shape. Okay, so this is like almost like a dendritic tree of a neuron, isn't it? So it's basically called a diffusion limited aggregate. Now, we think that diffusion limited aggregates and also Lindenmayer systems don't just generate nice, pretty dendrite shapes and axon shapes and nice kind of artificial neurons. We think that what diffusion limited aggregates and Lindenmayer systems or string substitutions are doing reflects fundamentally how neurons work. They reflect fundamentally how the entire brain works, and they reflect fundamentally a key building blocks for creating true artificial intelligence. Okay, so okay, let me explain another point. Okay, it is to do with perhaps the most fundamental idea in artificial intelligence and the most fundamental idea in machine learning. Okay, so what we have is basically like a forward tree growing mechanism of like Lindenmayer system, logical derivation systems, growing trees into Lindemeyer tree space, or logical space, or language construction space, or formal axiomatic system logic, mathematical proposition space. Okay, so it's like a forward growth mechanism pushing forwards, and this diffusion limited aggregate system is like a backward chaining system. Okay, of sticky growing backwards. Okay, we think these are fundamental complementarities to how the brain works. Okay. What is the most fundamental idea in artificial intelligence? I'll tell you what it is. And why is it the most fundamental idea? Because in the main textbook on artificial intelligence in the world, used most undergraduate, graduate, postgraduate, postdoc courses, okay, it's called Artificial Intelligence, a Modern Approach. It's written by Stuart Russell and Peter Norvig. Okay, this idea comes up again and again and again in the first kind of 10, 12, 13 chapters. Okay. In different guises. The basic idea is this idea of a forward search into space and a backward chain. Okay, so the diagram from the book, you have a start kind of region, the start point, and you basically branch out, you see, search out into space. Then you have the goal and you backward chain backwards. Now, this idea is kind of described in some of the early chapters as kind of abstract search into abstract search space. But also in chapters on gameplay, basically the start point is basically the position on a chessboard. Okay, so you can basically search forwards into different moves you can make on a chessboard, and the goal obviously is checkmate. You want to win the game, so you backward chain from checkmate positions, and where it meets, that's your path, that's your winning path. Or there's another chapter on robot situational calculus. Here's the robot. Where it is, and that's where the robot needs to be. So you forward chain all the things robots can do, and then you backward chain to where you want the robot to be, and then where the two meet, that's your path. Or it's also the same idea, forward search, backward search, in terms of logical propositions, first order logic, second order logic. But you see, it's the same basic idea, and we think this basic idea is exactly Lindemeyer systems, is exactly logical derivation, and the backward chaining goal aspect is exactly like diffusion limited aggregates. You see, so we think, and we'll kind of consolidate this idea as we go along, that what neurons are doing, a single neuron is inherently doing, it's basically animating, it's basically doing the most fundamental algorithm in artificial intelligence. Do you see the power of neurons? There's a most fundamental algorithm in artificial intelligence, this forward chaining search and this backward chaining search. And a single neuron is fundamentally doing that algorithm. Okay, now what's the most fundamental idea in machine learning? Now, the reason why I say it's the most fundamental idea is because Pedro Domingos, who's a professor of machine learning, he wrote a very good book called Master Algorithm. I mean, I recommend both of these books. I mean, the first book is a telephone directory. It's about that thick, and you've got to be really interested to read it. But Master Algorithm is very accessible, very good book about machine learning. In terms of foundational ideas, okay, the first few chapters, he introduces this idea of he's saying that basically, the most simple idea, most foundational idea he covers is this idea of just basically, you want to predict something. You form basically what he calls an n tuple. So you take one factor and you see how that factor predicts, something you want to predict. And then if it doesn't work, you take two factors and you do a two tuple, etc. Then you combine three factors, and that's called n-tupling. What basically you're conjugating, you're saying this factor and that factor and that factor and that factor, and how does that predict what you're trying to predict? Okay. Then he goes on to say that this isn't good enough, because basically he says you need disjunction, you need basically conjunctions, tuples, but you need disjunctions of conjunctions. You get my drift? So basically you need a conjunction, and then you need that conjunction or that conjunction or that conjunction, a disjunction of conjunctions. But that's exactly what we described neurons as doing earlier on. You see, the actual patches are forming conjunctions, and the branches are doing disjunction. So do you see, a single neuron isn't just a simple linear summation device. A single neuron pyramidal cell is actually inherently doing the most fundamental algorithm in artificial intelligence, according to the main textbook. And it's doing the most elementary, most fundamental operation in machine learning. So that's the power of neurons as the new kind of for the 21st century. And it's really the building block of this new generation of artificial intelligence. do you see the power of these, what I'm talking about? It's not, the overall artificial intelligence algorithm and the overall intelligent machine learning device. It's going to be really powerful and stuff, but the actual building block, the actual atom of the actual artificial intelligence is doing in a fractal way the entire device. Okay, that's like magic, isn't it? It's like a new, it just blows away existing ideas of what artificial neural networks should be. Yeah. Okay, so that's kind of like in schematic form, the kind of forward emanating process and the backward chain kind of meeting, and then kind of like where it joins, that's your path, that's your solution. Now, okay, I'm not going to talk that much about the fractal brain theory, because basically we're going to concentrate this on kind of new findings in neuroscience and on machine learning and artificial intelligence. But what I will explain fairly quickly is that this new neuron knowledge allows us to show how a single neuron doesn't just do the most fundamental artificial intelligence and machine learning algorithms. A single pyramidal cell, in effect, I can show works like an entire person. Now, that's completely outlandish, isn't it? How can a single neuron be like an entire person? Well, if I show how an entire person, what we're doing is like a Lindenmayer system and a diffusion limited aggregate, you see a mapping, there's a symmetry between what a neuron is doing and then what an entire person is, what a person does. Okay, so let me go through this. We need to go through a bit of architecture, brain architecture. I was going to go through this, but I mean, just to make time for all the rest of the talk, I mean, there's quite a bit more information to get through. But basically, the fractal brain theory became something much more. It's not just a theory of the brain anymore. It's a theory of the genomes. It's what it is. It's become, okay, let's go through this quickly. It's become a unified theory of life and intelligence. That's what it became over the past 10 years. So there's a way of looking at, okay, I'm going to show how a neuron works like an entire person. There's also a way of looking at how a gene also works exactly like a neuron. Okay, so it's gone much deeper. It's gone into life science. It's a unified theory of what's life and intelligence. It's like, it's like Einstein's E equals mc squared. Okay, he showed a fundamental symmetry and invariance between matter and energy, these fundamental aspects of the universe. Now, life and intelligence are also fundamental aspects of the universe and life and what we see around us. And the basic, what I'm saying is, life and intelligence, genes, gene regulatory networks, genomes, development, ontogenesis, evolution on one side, learning, creativity, thought, behavior, brain, neural networks, neurons on the other side, are basically two sides of the same coin. Okay, so that's what the theory has become. And that's what, okay, I don't have time to go into the details of this, lots to unpack and explain there. What I will explain is the idea that a neuron is working like an entire brain, like an entire person. I can do this fairly quickly because I've already explained Lindenmayer systems and diffusion limited aggregates. Okay, that is basically back to where we were. That's a brain, and that's your cerebral cortex flattened out. Okay, so the cerebral cortex, okay, that's one of the flat sheets, and they're demarcated into these different zones. Okay, so this kind of mauve area you see here, this kind of mauvey area, is the front part of your brain, the front part here. And that's the back part of your brain. And like a patchwork quilt, you see these numbers. These are called Brodmann areas. So these are like different Brodmann areas. These numberings perform different things. So this is kind of higher cognitive function. That's the kind of emotional processing. That's to do with primary motor cortex, premotor cortex. These are primary visual cortex. Now, okay, the front part of your brain, okay, that does most of the thinking and the doing and the emotional processing. Okay. Now, all those parts are linked up with a part of the brain called the striatum. Okay, so imagine all the parts of your brain which does things like thinking and active things are basically linked up. They form what's called closed loops with this part of the brain called the striatum. So that you can see in this kind of diagram, kind of like where it's situated. Now, each of these parts of the brain, okay, will form. Okay, that's a monkey brain, and because basically most of the data is from monkey brains, you see these markings on the front, these numbers completely correspond with these closed loops. So these are loops. Okay, this is the stratum, the main body, where I'm shaking my cursor. And these are like, this is cerebral cortex. It forms closed loops, which means that a patch of cerebral cortex in the front part of your brain will basically project into the stratum, and then the stratum will project back to that part of the cortex. Now there's a central area of the cortex and a central corresponding part of the stratum. Now it inputs to that area and it projects back to the central area, but it also takes inputs from some of the surrounding areas. Okay, so it's basically forming a closed loop, like a wheel. Okay, so it inputs data, and then it loops back on itself, and then it projects the kind of next state. So it kind of projects forwards in time. Okay, so there is, okay, forget that, that's a cerebellum. We won't have time to discuss that, but that's your stratum, and that's your closed loop. That's like a cerebral cortex, you see, and basically you can see it projects in, then it loops back again. Now, the stratum works with what's called a chemical called dopamine. Okay, so if the dopamine flows, then the stratum works. If the dopamine doesn't flow, your stratum doesn't work. So Parkinson's disease, you lose your dopamine neurons. Okay, if you take certain drugs, boost dopamine, like cocaine, amphetamine, even caffeine will boost your dopamine. And when your dopamine is boosted, your brain works faster and more fluid. You know, like talking to coke heads, they talk very fast and they talk a lot of nonsense, but they talk very fluidly. Okay, but when a dopamine doesn't flow, then you kind of freeze up. Okay, so dopamine is really, really important. So you lose your dopamine, you lose your stratum, then you basically, you can't move, you can't act, basically. So it's okay. Now okay, there's more complexity here. I'm just going to a tiny bit of complexity. Basically, there's three pathways, but the most important for our purposes is what's called a direct pathway and an indirect pathway. The direct pathway into the stratum basically is your go pathway. It's basically, you know, the loop that kind of turns the behavior, makes your behaviors go forward. The indirect pathway is the stop pathway. Okay, now specific neurons that feed into the stop pathway are called pyramidal tract neurons. Okay, this is A is an example of a pyramidal tract neuron in the cerebral cortex. You see, it's very simple. The branching is very not so complex and not so much processing in those dendrites. But with the direct pathway, it's actually really, really complex. Can you see? And then that projects into the stratum. Now, these pathways, the indirect pathway, the stop pathway, and the direct pathway, they're actually separate. So they don't mix. Okay. Now, okay, I'll go into another level of detail because it's important for a later part of the talk when I explain how the brain does algorithmic processing. Okay, it's a tiny bit more detail, and it's to do with another demarcation of the stratum into two areas called matrix and patch. Okay, so okay, we've got a separation between direct pathway and indirect pathway, a kind of go pathway and a stop pathway. Now there's another path demarcation between what's called matrix and patch. One of the frustrating things about neuroscience is that the facts change. Okay, it's made like quicksand. You think you've learned some fact, and then it changes. Okay, I'll give you an example. Okay, this is so frustrating. I'll give you an example. 30 years ago, I read a book called Synaptic Organization of the Brain by Gordon Shepherd, and he writes that okay, the indirect pathways and the direct pathways are only found in the matrix. And he adamantly says explicitly they are not found in the striosomes or patch of the stratum. Then 30 years later, I read, or actually 25 years later, I read in the same book, okay, Gordon Shepherd's Synaptic Organization of the Brain, with a co-author, okay, young blood, okay. Now it's completely changed. Now also the striosomes also have indirect and direct pathways. Well, to cut a long story short, it means that basically there's four separate pathways through the stratum. Okay, can you see this diagram here? Okay, basically that's a cross-section of the stratum where I'm shaking my cursor of the rat. The blue represents the striosomes and the kind of orange represents the kind of what's called matrix. So the indirect pathways, the stop pathways and the go pathways, direct and indirect, actually interpenetrate both the striosomes and the matrix. Okay. Now, the critical thing is that it's only the striosomes that activate the dopamine neurons. Okay, this is critical. You see, the dopamine neurons is actually what drives the dopamine pathway, you know, the stratum to go round and round in circles. And it's only the striosomes that actually drive the dopamine neurons. Now, the striosomes tend to be connected with the emotion centers, which means hypothalamus, the amygdala, you know, the emotion processing centers. The engines of your mind tend to, in the front part of your brain at least, project into the striosomes. And it's only the striosomes that drive your stratum, through the dopamine neurons, you see. what it means is that these four segregated pathways are doing something very, very quite special. What they're doing is, okay, look, it means in computer programming language, it means that while the dopamine flows, okay, then you do what you have to do. The dopamine flows if some Boolean condition is met, which is handled by your, these Boolean processing dendrites doing symbolic processing. And the stop pathway, the indirect pathway, what it's doing is basically saying, keep doing it while the dopamine flows. Okay, you do your thing, the wheel turns, dopamine's flowing, you're going towards your reward, you're chasing food, you're chasing whatever you're chasing. But when the indirect pathway is like saying, repeat until some condition is met, i.e. you see a stop sign, you see a danger sign or whatever, or you feel intense pain, you have to back off basically. Now, it means that basically there's a way of understanding the stratum in terms of these computer programming constructs, while Boolean condition, repeat until. Now, okay, that is a bit of complexity for the end of the talk, okay, when we deal with a very hard subject called neuro-algorithmics. Now, back to Lindenmayer systems, it means what the stratum is doing is basically it's doing that mapping, it's doing that string substitution. It means that there's a state in the cerebral cortex. The loop is basically pushing into the stratum. If the dopamine flows, then branch into the next state. And if the dopamine keeps flowing, like the Lindenmayer tree growing forwards into space, you explore into what you need to do. Do you see? So basically the mapping, the closed loop of the stratum is effectively doing that Lindenmayer string substitution or mapping. And you're mapping in time. So time 1 + 1 + 2. You're basically you can't split yourself into two people, but you can basically make a decision to go down a tree of exploration. You see, and then certain rewards, certain things will reward certain behaviors. Okay, now the next thing to explain about human behavior is that obviously certain rewards, certain things are rewarded, and certain rewards will basically kind of encourage certain behaviors. Now dopamine is not just the chemical that makes behaviors work. Dopamine is also what's involved in what's called a pathway of addiction. Okay, so dopamine doesn't just allow behaviors to unfold. Dopamine also reinforces behaviors. Okay, so the kind of recent finding from 10 years ago, okay, this is quite recent. Basically, if basically, okay, you basically see an unexpected reward. If I'm like a tramp, I wander around the streets of London. If you see an unexpected reward, like a £10 note on the street, you get a rush of dopamine. Your dopamine levels will rise. Okay. Now, in the stratum, when your dopamine levels rise, then physically your neurons from your cerebral cortex into your stratum get strengthened. So it's like a chain. If that loop is like a neural chain, it's like physically that chain will get strengthened. The synapse from your cerebral cortex into the stratum is physically long-term potentiated. Now, conversely, if you were expecting a £10 note in a certain spot and you feel disappointment, then the dopamine level drops. Then the connection is weakened and the chain weakens. And with sufficient weakening, you don't do the behavior anymore. It's like a machine, isn't it? Like a machine. Okay, now, by what criteria does do we learn how to see what's rewarding and what's not? Well, we go back to our diffusion limited aggregates. Okay, so this is the diffusion limited aggregate aspects. So in this diagram, we're basically showing the engines of the mind. Okay, so to cut a long story short, in psychology, that's what's known as unconditioned reinforcers. Okay, so but it's unconditioned because you're born with them. Okay, so these are things like orgasm, like, basically you're cold, then you're warm, you're hungry, then you're kind of fed. They're rewarding, okay, they're rewarding, and basically intrinsic. You'd have to learn these unconditioned reinforcers. Now, which parts of your brain actually encode these unconditioned reinforcers? It's essentially your hypothalamus and your amygdala and what's called certain parts of your cerebral cortex, orbital frontal and subgenual cingulate cortex. I mean, I can go on, but basically these are the emotion centers of your brain. The critical thing is basically these unconditioned reinforcers, you learn what's called higher order higher order conditioned reinforcers now. So I'll give an example to explain what it means. And it's like a diffusion limited aggregate. If these unconditioned reinforcers are like sticky points, okay, to which behaviors get stuck. Imagine a baby. Okay, baby is born with no idea of rewards or money. Okay, back to our £10 notes found in the street. Now, a baby learns of a sensation in its mouth. It's hungry. It learns that a certain sensation in its mouth, kind of food, maybe mother's breast or, kind of spoon in its mouth, then it's not hungry anymore. Then it learns that maybe the baby food comes from a jar. Okay, and it backward chains. And then over time, it learns that that baby food came from a supermarket. And then baby, a kind of contrived explanation. And then it learns basically that mummy pays money to the cashier. And then over time, baby gets older, learns about money. Then over time, you learn about getting a job and you learn the value of money. What it means is that, like that diffusion limited aggregate we saw earlier, basically you form a backward chain from all your unconditioned reinforcers that are hardwired into your brain at birth. And you form a backward chain, this kind of diffusion limited aggregate, like we saw earlier, of all your values, or everything you find valuable, everything you find aversive, and it grows like a diffusion limited aggregate. So your entire web of meaning and affordance and salience is growing from these unconditioned reinforcers, growing backwards as you go through life. And one of those will be money. Okay, and money satisfies lots of kind of unconditioned needs. And then what happens in life is basically you have that backward chain, and then you have this forward dopamine-driven stratal Lindemeyer system tree growing forwards, and the two intersect. Do you see? So it means that basically we show how the human being is like a Lindemeyer system with the stratum dopamine system branching forwards, projecting forwards into a space of possibilities, and how the idea of unconditioned reinforcers and learning higher order reinforcers is like a backward diffusion limited aggregate chain. Then what you're basically showing is like the entire person is working like a neuron. So it shows how this, what's called a perception action cycle, you show how it works. Basically, it's a Lindemeyer perception. You perceive something, you act, and the act generates a perception, but you want to generate those perceptions which lead to reward, and you want to avoid those perceptions which lead to pain, you see. And it's just like a neuron branching forwards, and then a dendrite growing backwards, and the two intersecting. It's like our basic fundamental artificial intelligence algorithm, forward chaining and backward chaining. Okay, so we have a view of neurons now, which is very, very just a million miles away from the existing kind of state of the art. So that is kind of like the kind of first way this new research kind of really just answers lots of questions in machine learning. We'll kind of plow on. Okay, in this diagram here, we'll cover some of these issues, then we'll take a break and we'll take some questions. Okay, we just cover the first point, and then we'll take some questions. Now, a critical issue in the next critical issue in artificial intelligence. Okay, we're kind of moving on now. Is the question of the sub-symbolic versus symbolic. This is very topical right now. You kind of read computer artificial intelligence journals. It keeps recurring, and it also interviews some of the big names. Now, there's this idea, it's by Nobel Prize winner Daniel Kahneman, that in the brain there exists two levels. He calls it system one, okay, sub-symbolic, which is visual processing, basic auditory processing, and he calls system two like reason, basically, and he says this is a two-tier thing. Now, what we show with the new knowledge of neurons is basically it doesn't exist. It's basically misconceived. Once we show that basically the sub-symbolic level is effectively acting in a symbolic way, it's basically doing these complex symbolic operations like XOR, like add, disjunction, conjunction, etc. And we're also showing that basically the actual physical structure of neurons is effectively like doing the kind of like physical structures of symbolic processing, i.e. language. Okay, so it means that basically the what's called sub-symbolic is effectively symbolic. There's a continuum. It's not one level, one thing and another kind of discontinuity. It's rather better seen as a complete continuum. And we actually look at the brain, the hierarchies, what we see is kind of continuums, what we see is symmetry, and what we see is, kind of like these kind of like essentially discrete symbol-like processing operations going on even at the, not just neural level, even at the level of patches of dendrite, as we showed earlier. You see, so the complete idea of sub-symbolic versus symbolic is completely misconceived. Now, the idea of, okay, another major question is to do with the continuous versus discrete. Now, this is really important because backpropagation is this dominant algorithm. It's called, and it works using the traditional calculus, which is, what you learned back in school. It deals with smooth graphs. So it's basically differentiation. It uses, traditional Newtonian Leibniz differential, calculus, basically. Now, Geoffrey Hinton, Yann LeCun, Joshua Bengo, they're the biggest names in the most dominant form of machine learning, artificial intelligence called backpropagation. Now, Geoffrey Hinton is the godfather of backpropagation. He's like leading light. Now, Yann LeCun said, I can quote him, he said, reasoning, how do we make it compatible with gradient-based learning? Reasoning, how do we make it differentiable? That's the bottom line, he said, unquote. Okay. And Joshua Bengo also believes, I mean, he's saying that, we necessarily have to reduce the symbol processing aspect to continuous backpropagation, because there doesn't exist the kind of discrete scalable algorithm like there is for the continuous, i.e. backpropagation. And Geoffrey Hinton, he kind of flips and flops over the years, but he kind of says the same thing. Now, all three of these are not advocating a hybrid approach. They're saying that backpropagation can do all of it. They're saying they can subsume the discontinuous, the symbolic, the discrete with the continuous. Do you see what's happening? Okay, I think they're completely mistaken. And given the new view of neurons, you see, it shows basically, again, it's completely, it doesn't make sense. If you understand the way neurons work, it's not differentiable. Now, differential equations does, like continuous phenomena, but as we showed earlier, what neurons are doing, even at the synaptic level, is something very discontinuous. It's doing Boolean logic, essentially. It's doing combinatorial logic. Now, okay, Francois Chollet is one of the guys, a young guy. He's actually, he's one of the guys who says sensible things in the world of machine learning. He works for Google. He's really talented. He actually wrote this thing called Keras, which is basically the interface that Python programmers use in order to use what's called TensorFlow. I think it's also works with PyTorch, Facebook's thing as well. It's basically most machine learning people use a lot. Well, I don't know, most. I mean, a lot of people use his software Keras to basically conjure up all these different machine learning architectures. So he's got kind of like really good view of an overview of things because he's in a privileged situation. He says neural networks are poorly suited to discrete problems that people who are good enough at deep learning to realize its limitations are too invested in its success to say so. Kabam! That's really, kind of like, really kind of revealing, because he's an insider. He's actually working with these deep learning, backpropagation professionals. Okay, quote, a lot of well-funded, large-scale gradient descent projects get carried out as a way to generate bombastic press articles that misleadingly suggest that human-level AI is perhaps a few years away. Many people have staked a lot on this illusion, but it is still an illusion. Okay, fantastic. He's actually telling the truth. Amazing, because he's not so invested in deep learning. Okay, so what we think is basically there is a better way of doing it. Now, Francois Chollet also believes, he believes in a hybrid approach. He believes in mixing the symbolic and sub-symbolic. So he's kind of like taking Daniel Kahneman's interpretation. And the most vocal critic of backpropagation, a guy called Gary Marcus, he also advocates a hybrid approach. But you see, there's a third approach. And it means the third approach, we can subsume everything using the discrete. And it's actually based on how neurons actually work, which is in a sense symbolic and discrete. We think we can subsume all of it, all machine learning and artificial intelligence and even neuroscience into a discrete format. Before I open up to questions, let's just quickly just before we take a break, this goes into a wider question of what is science. Okay. So what is science as it's been done for the past few hundred years? Now, okay, so the example of, okay, where do differential equations come from? Okay, so basically we can trace the lineage of ideas. So in the kind of like Renaissance, Johann Kepler and Tycho Brahe. So basically, Johann Kepler had to join the dots. Tycho Brahe had the dots. He had observational data of the orbits of the planets, okay, in the sky. And Johann Kepler's big innovation was elliptical orbits. It sounds completely obvious now, but it was people thought orbits had to be perfect circular. Elliptical orbits, not perfectly circular, but elliptical. Along comes René Descartes, and he formulates, probably derived from Arab Muslim scholars, kind of Cartesian geometry. So now you can describe the elliptical orbits using his kind of analytic geometry, he'll call it, analytic geometry, the father of Western philosophy, René Descartes. You can actually use equations now to describe those elliptical orbits. Now, along comes later on, a couple of generations later, Isaac Newton and Gottfried Leibniz around the same time separately formulated the differential calculus, which is what deep learning backpropagation is based on. So now you can basically describe the orbits of the planets as elliptical orbits, but now you can describe the change in time, the dynamic of the orbits of the planets, the differential over time. Okay. Now that is how science has been done for the past several hundred years. Okay, so that's basic science. Okay, the dots are much more complex. The differential equations are far more complex. You might have a statistical science, in which case you're not joining the dots, you're corralling the dots. But it's still the same idea. You've got lots and lots of dots, and you have to somehow link them all up into some kind of succinct mathematical description. Now, the idea is basically there is an equivalent and just as valid and perhaps even deeper scientific language, which actually subsumes everything we see here, i.e. continuous science. And it's to do with the work of two of the most clever people in the 20th century. Now Principia Mathematica by Bertrand Russell and Alfred North Whitehead is one of the most genius, one of the greatest intellectual achievements of the 20th century, up there with Einstein's general relativity and up there with the formation of quantum mechanics. Now, what is Principia Mathematica? What is it? Okay, so what did they do? I'll tell you what it is. Bertrand Russell, okay, won two Nobel Prizes, very smart guy. Alfred North Whitehead, one of the kind of geniuses of the 20th century. What they did was they reduced all mathematics, all of it, every single scrap, every bit of mathematics into set theory. Set theory is exactly like you learned in school, utterly simple, and that's called discrete mathematics. Now, mathematics actually reduces to something even simpler, which we talked about earlier, called formal axiomatic systems, which is the string substitution systems we talked about earlier. Now, do you see where I'm going? Look, because all mathematics reduces to discrete mathematics and ultimately reduces to formal axiomatic systems, the question is, if you convert any science to discrete mathematics, is it no longer science? Well, of course not, because it's equivalent. And in fact, discrete mathematics, formal axiomatic systems can be seen as the deeper level of mathematics. What we propose is that basically there is a deeper level of mathematics which is perfect for describing the brain and actually creating artificial intelligence. And that the traditional calculus, which is what backpropagation is based on, it doesn't do the discontinuous. It doesn't do like what real neurons are doing, like we showed earlier. It doesn't really do recursively nested hierarchical structure. So what we propose is basically a new way of doing artificial intelligence that subsumes the kind of sub-symbolic in this new language, which basically unifies the sub-symbolic with the symbolic, which is the third way. Okay, so this is what we're going to talk about in the second half of the talk. So just to finish this first section, we've gone off much longer than I thought the first section would go on for. Okay, so just go through some ideas from some of the leading lights in AI, okay, and kind of philosophy of AI, I suppose. Okay, the critical idea, concept, and language needed to create true AI. Okay, David Deutsch, a quantum physicist and does a lot of work on quantum computers. He said, it is plausible that just a single idea stands between us and the breakthrough that will produce true AI, but it will have to be one of the best ideas ever. Rodney Brooks, who was longtime director of the MIT lab, AI lab, he said, a design principle, concept, or language may revitalize the mind sciences in the 21st century. Melanie Mitchell, who works with Douglas Hofstadter, who wrote Gödel, Escher, Bach, She said recently, the dream of neuroscience is to come up with the high-level programming language of the brain that allows us to make sense of what the system is doing in terms that we can understand. So in the second part of the talk, we will basically go into this, what these people are suggesting is the case, and we'll describe exactly what that is. The basic, most critical idea is symmetry, and the language we'll describe is our discrete language, a new discrete mathematical way of describing the brain and mind. So anyway, we're going to maybe take a break now for some Q&A. Okay, so that was a pretty long section one, actually. I didn't realize it was going to go so long. But anyway, time to make a cup of tea, and I'll take a few sips of water. If anyone has any questions, then ask now, forever hold your peace. Okay, Oliver, just unmute yourself.
Sorry, yeah, it took a while to find the button. So many questions. It's hard to pick one, but
oh, tons of material covered in that even in quite a short space of time. Just
yeah. Minutes. So I'm going to stay quite high level, and so what I'm questioning is you're citing a lot of like neuroscientists and AI guys, machine learning. What is essentially your contribution here? Is it? I mean, I know you sort of coined the fractal brain theory. Is no one else doing that? Like, is because it seems like the neuroscience is like arriving at this idea of a fractal neuron and so on. So is it that the neuroscience is catching up with your fractal brain theory, or what's happening there?
No. I mean, this sounds kind of like a bit bombastic. It sounds a bit arrogant, but yeah. I mean, Oliver, the one advantage I have is basically, years ago, I was going to do a PhD. I went to Imperial College because back 30 years ago, that's the main center of AI basically in the UK. And I was going to do a PhD. I told my mum, basically, I was really I was very bad at school. I was constantly playing truant and stuff. And I told my mum one time, just before starting university, I said, "Mom, I'll be good now because I'm studying something I really like and stuff. I'll attend lectures and I'll do all my work and stuff." But I learned pretty quickly. Actually, I bought 2 books. They're called Parallel Distributed Processing, volumes 1 and 2, the summer before I started university, and I read, basically the latest cutting edge neural network stuff, and I thought, my God, this is not artificial intelligence. So years ago, 30 years ago, I decided what was happening is not true. This is not going to lead to true artificial intelligence. This is not going to lead to an understanding of the brain. And who was one of the authors of one of the most prominent chapters in, Parallel Distributed Processing volumes 1 and 2? It was Geoffrey Hinton. Okay, so he's like the leading light of AI now. So I took a totally kind of divergent course. And one of the reasons why I'm able to do what I do, Oliver, is because I didn't do a PhD. Now, kudos to people who do PhDs, but it's a very narrowing of the mind. Okay, let me explain. Basically, a career in academic, governmental, corporate research involves putting yourself into a box. I'm sorry to say that, but it's what it is. Demis Hassabis talks about it's great that we need to be multidisciplinary, but he just says basically, it doesn't happen in academia. Basically, multidisciplinary means you do a workshop in the summer, multidisciplinary workshop, and you kind of sort of multidisciplinary for 2 weeks. Then you go back to your university and you're back to your box again. Yeah.
Yeah.
So what I think is happening is basically that neuroscientists don't have the knowledge of computer science. Neural network people just don't know this new neuroscience. And even neuroscientists are unaware of this new dendrite research. It's crazy. I mean, top neuroscientists in DeepMind, I mean, he appears completely unaware because he's saying that a new, learning algorithm will not emerge from neuroscience. Do you see what I mean? That's the top neuroscience at DeepMind. Christoph Koch, one of the great top neuroscientists in the world, he says, don't look to neuroscience for innovation or ways of making your machine learning faster. He said that in a panel earlier this year. But obviously, when you learn this new dendritic research, do you know what I'm saying?
Yeah.
He did some of the most important research on dendrites 30 years ago, okay? But it seems with all his admin duties, he's not kept up with the latest research. So what I think is happening is basically that specialization, if the solution to the problem involves thinking out of the box, the problem is that a career in academia and corporate research lab, you're inherently putting yourself into a box. Yeah. Do you see what's happening?
Yeah, yeah. So supplementary question. So if you're saying we're going to base AI on ever more accurate models of the fractal neuron, then will it be limited in the same way that human intelligence is limited? Or what's going to be the superpower? Like if it's based so accurately on the way that a human neuron works.
I mean, we are basing what we're doing on real neurons, but the thing is, we can transcend the limitations of biology. So what I think is basically, we think that there is only, we think intelligence is really, really special. It's not a kludge, it's not some point in mind design space. It's something very, very special about what intelligence is. That by studying the brain, we can actually extract the essence of this very special thing. But once we have that, then we can basically use it to create artificial intelligence. Once we create it in a machine, we can speed it up. It doesn't have to sleep. You know what I'm saying? So I think we can create something very, very utilitous. I mean, in terms of super intelligence, all that kind of like super intelligence will take over the world stuff. That is, I don't see that happening, because in the brain there are all these kind of like control mechanisms to stop that happening. Do you know we are basically slaves to the hypothalamus. We're like slaves to this tiny part of the brain. It's very hard for our logic centers to override the hypothalamus. So I see these super intelligence is emerging, and I see dumb humans as being like the hypothalamus, being controlling these super intelligences, and we in turn being controlled by our real hypothalamuses. So I see basically this information leading firstly to creating very utilitous technology, but later on it will create kind of like intelligences far way beyond what humans are.
I love that, how you just very quickly formulate the analogy of the thalamus and the human and the AI. It's a very cross-paradigmatic view you have always of this kind of fractal, like.
Yeah. I don't see computers, artificial intelligence taking over humanity. I see a continuum. I see, years ago, I was sitting in a restaurant in London. I saw basically a continuum. I saw basically, I was sitting in a restaurant. I'm in a city. I'm in London, but below me is the sewers, and there's rats, and there's germs and stuff, and there's basically primordial bacterial life, and above that is kind of human beings and dogs and cats and stuff, and then there's high life, and then there's kind of like penthouses and stuff, and people controlling the world. But I saw it as a kind of continuum. You know what I'm saying? So I see the growth of what's happening on this planet with artificial intelligence continuing that kind of trend, where basically we still play our games, the hypothalamus still reign, and is still serving that basic survival function, that's basic reproductive loop. And I think that I see that going on until the end of time, really. That's why I see things. So a kind of continuum rather than computers taking over humanity. Anyway, any other questions?
Yes. What about?
So who's that? Oh, Jerry. Fantastic. Good to see you again.
Good to see you. This is so amazing.
It's like sorry to interrupt. It's like a real Philip K. Dick novel, isn't it?
It is really. And I just get the feeling that getting here, seeing your lecture or thing here is like being in the really really into it. But to the question, how do you put the factor of time within the workings of neuron, putting aside if fundamentally time is discrete or not? Let's say that in the still macro level of dendrites working, you could kind of assume that time is non-discrete. So like in computers, you have the clock that is running the operations, while the starting from a layman's information, you could think that the neurons and dendrites are a bit kind of random in that sense of how much time it takes for certain chemical and the process.
We absolutely have a solution for you. Basically, later on we'll show our language is actually it's quite clever because it actually reconciles the discrete with the continuous. I know it sounds okay. It sounds like a kind of contradiction in terms, doesn't it? But basically, I don't want to do the next part of the talk in Q&A. So we're basically going to answer that when we actually go through our language. The language is discrete, but there's like a slide factor. There's a slide factor which can also be discretized, which then does the continuous to however level of precision you need. Does that make sense? But we'll go into it in detail in the next section of the talk. Yeah.
Okay.
The short answer is basically waves. You got discretized. You got discrete structures. Discretized binary trees. Then you have wavelets. So you have a wave that's on the end of a binary tree. That's like a wavelet. You chop up the wave. So that's continuous, but it's still discretized. Now the trick is you have a slide factor that's actually built into the language, so that the wave can actually phase shift, and that's the answer. So it's discrete. We can have it as continuous to however level of resolution you want to throw at representing the continuous section. In the rat brains, but also in the human brains, it's been found. This is exactly what happens. It's called theta phase precession in the hippocampus. You have place cells which seem to register the rat being in a certain place, but it's what's called theta precession. So as the rat or mouse or human being moves along the location, that fixed discrete location, then the actual theta, the actual firing of the place cell will shift along the phase of the theta wave. Does that make sense? And I'm saying we can directly model that in our language. And I'm saying it's universal. It's not just hippocampal theta. It's basically all the brain waves. It's basically all aspects of time. We can basically phase shift in time. We can also phase shift along spatial frequency as well. That's a bit technical, isn't it? But we'll explain it more in the next section of the talk. Any other questions, or else we'll roll on?
I've got a question.
Oh yeah.
All right. You mentioned some that neurons and have been found to be like performing some of the same functions of AI, and I was just wondering, is that because the AI is being built by brains that are created by with a lot of neurons, or is that more like it's just like the nature of intelligence?
It's basically the nature of intelligence. I mean, the fractal brain theory describes that the brain is a perfectly symmetrical architecture. The thing is, look, the new information on neurons, only came out in the past 5-10 years. The book I showed you came out 2016. I mean, I'd actually read the previous edition. The new edition, 40% is all new content, and the rest of the 60% is all rewritten. So basically, the last edition was that thick, and the new edition is that thick. It's all new information. Now, the thing is, the fractal brain theory predicted what a neuron would be. So it's not like, it's almost as if the new information is just filling what the fractal brain theory anticipated. And during the lockdowns in London, when I was covered for my family, I always time to catch up when I was neuroscience literature. And as I was reading the Dendrite book, it was almost like magic. It's exactly what I was predicting. I know it sounds like, some kind of blow my own trumpet kind of thing. I mean, I gave lectures years ago before this information was even discovered, which actually anticipated all these findings, this backward chaining and stuff. So I think it's to do with the fact that there's a symmetry, there's a basic pattern which is found in neurons. It's found in how people work. It's found in how true artificial intelligence works. And it's also, this pattern extrapolates to the universe. Okay, I'm kind of like, that's a bit highfalutin. It's kind of connecting the talk 2 weeks ago. The notion of basically the universe as a cosmic tree, the universe as a giant brain, the universe as ontogenesis. So basically this fundamental tree structure, it is literally cosmic. It is a cosmic fractal. And the fact that it's represented fully in our behavior of an entire person, it's also represented in a kind of a single neuron and many levels in between: cortical columns, macro columns, cortical patches, stratal cerebellar cortical loops, right up to the cosmic level. You know what I'm saying? So I think it's a very profound and it's a simple thing, isn't it? A tree structure, roots growing back and a tree growing out. I mean, you see it, trees are everywhere. And I'm saying it reflects something fundamental in basically the universe. So yeah, absolutely, yeah. Any other questions? Does it answer your question, Matt?
Yes, thank you.
Okay, so really cosmic. I sound like a tree-hugging hippie tree lover, don't I? But no, trees are really important. Okay, so any other questions, and then we'll kind of continue, I suppose. There's loads more material than 2 hours. I kind of hoping to squeeze everything into 2 hours. So I'm going to zip through as much of the second half as I can. Okay, so anyway, shall we just hop on to the next section of the talk? Okay, so basically, I'll screen share again. So basically, we're going to go to okay, where we left off in the first section is this critical language and critical idea. The critical idea is symmetry. I'll just quickly go through this. Okay, so these are trees. That is a binary tree. So binary trees basically a binary branching. We think the critical idea involves binary trees. We think the binary tree is very fundamental. It's fundamental in mathematics. It's fundamental in computer science. Now look, what we propose is basically that we propose to merge discrete mathematics, obviously very powerful. All mathematics reduces to discrete mathematics. Okay. Now, all the relations of set theory and Boolean algebra, they are binary. All the structures of logic and Boolean algebra are basically binary tree structures. The nested parentheses in books about logic and Boolean algebra, what those nested parentheses are basically describing in linear format is essentially hierarchical binary tree structures. That's what essentially is going on. Okay, so we propose to merge the power of formal axiomatic systems and discrete mathematics with a way of representing space and time using binary trees. And now a very easy way of doing it is this. Okay, so that's a binary tree, that's a binary tree. You can see I rotate. Now look, what I've done here is the binary tree has split in a certain way to create like a grid, like a square. And I can recursively create a more high resolution grid. I can keep doing this to infinity. Now that's called a quad tree. Okay, this is actually one of the most fundamental data structures in computer science. This way of demarcating a 2D plane is essentially how the latest and greatest video compression technologies H.265, H.266 work on your smartphone, on your YouTube player. Basically, this is how there's a demarcating of your basically 2D video planes, okay, video frames. And also what's called wavelet transforms also use this way of demarcating 2D space. So it's actually very satisfying, isn't it? Because it actually very corresponds to a very tried and tested method in computer science. Now look, see, this is a binary tree, but we're representing time, or we're representing a list, we're representing a sequence in time, you see. So binary tree, binary tree, binary tree. This basically is a succession of these 2D frames, which could be like a flick cartoon, like a movie reel, or it could be patches of cerebral cortex, or it could be patches of cerebral cortex interacting with your stratum happening over time. Now, this is another binary tree, but this is unbalanced. You can see it's also a binary tree, but it's basically doing the same thing, but it's kind of unbalanced. Now, of theoretical interest is that, okay, Lisp, which is the first artificial intelligence programming language. Lisp stands for List Processing Language. Now, how Lisp represents lists is exactly in this way. It's exactly in this binary conjugating way. Okay, that's a bit of a geeky aside, but it's very satisfying. It's a very satisfying way of actually representing things, space and time. Okay, 2D space. Now, okay, what we talked about earlier, okay, about Jiri's question about the discrete and the continuous. It's basically, okay, your language is a bit clunky, isn't it? It's a bit like bit rigid and square. And, why can't we have the kind of continuous? Well, you can, look. So basically here, do you see this animation is basically, we're basically showing that, you know, what we showed in the previous slide is basically animated now. So basically, so it's the same thing, but basically you're shifting and sliding. The language is literally flexible. I mean, that's I was gonna do a newer kind of screen capture for this talk, but I never got round to doing it. Let me just reset my phone. I've got a new version here. Just reset, and then look. Just let me stop the screen share. Okay, stop the share. I've got a new version of the same program. So just let me. Okay. Oh, it doesn't work. It doesn't work. It doesn't work. Oh, what's going on? What's going on? Can you see that? Can you see the? Can you see the grid? Oh, I can't see the controls. I can't see the damn controls. Well, anyway, look. I can basically. You see, it's
I think if you turn your background off, it'll pick the phone.
Oh yeah, got it. Oh yeah. This is it's a bit confusing, isn't it? So basically, say I basically choose virtual background. Just turn it off. Okay, just turn off the. I have a green screen. Oh, what's going on? What's going on? Background and filters. Oh, what's going on? Oh, let me just. Well, can you see? Look, now it's sliding and scaling. Can you see that? It's sliding and scaling. You see, so literally the binary trees you saw earlier are scaling and sliding. Okay. Now I can basically is recursively doing it. So when the big square slides and scales, all the recursively nested squares do the same. Now I can also do recursively rotate. Now, normally that's not very useful, but it's just basically recursively adding the continuous into our binary discrete structures. So basically all the transformations, slide, scale, rotate, are actually inherent part of the language. And what it means is basically is that it's on the smartphone. So what I need to do is basically just install OpenGL on my workstation and get basically the main thing working on my workstation, so I can do a screen share. Okay, so that's a few hours of programming, which they've got around to doing. It just means that our language we're talking about, it's literally flexible. So Jury's question earlier, basically, yes, it is discrete, but because you know, the binary trees, they can flex around, they can literally they can slide recursively, they can scale recursively, get bigger and recursively. They can also rotate, they can also share, they can also do all the other transfer, invert, and you know, reflect as well. Okay, so basically it means that all your affine transformations are actually built into the language. Okay, so it actually handles the discrete and the continuous. Okay, so let me just proceed. Okay, so I'm going to screen share again. Okay, so that's the kind of like flexible aspect. Now, the other important part of the you know, figuring out how the brain works is this concept called symmetry, which has become a very hot topic now in machine learning and artificial intelligence. Now, just quickly explain the meaning of symmetry in the most kind of generic way. Okay, symmetry. What you learn in high school is an idea of symmetry that emerged during the Renaissance. Okay, so here we have the basic idea of symmetry you learned back in school. Okay, so get that as a square. You can rotate it 90 degrees or 270 degrees, 360 degrees around the center, and it looks exactly the same. You take the same square, you can reflect it on these axes in diagram B, so I can reflect it, and it looks exactly the same. That's the idea of symmetry you learned in high school. Now, the basic idea in symmetry is this idea of transformation and invariance. Okay, so the idea became extended over time. It is the idea that basically you transform something, but an aspect stays invariant. So it's to do with change and immunity to change. So you're changing something, but something stays immune to change. Something is invariant to that change, and the changes are the symmetries. Okay, so in the top of this diagram, basically you got the shape of a square, and it transforms into a kind of hexagon, a circle, and a star, but the color stays invariant. That's the invariant aspect. Now on the bottom you have a square, okay, but now the square shape stays invariant, but the color changes. Okay, so that's the basic, most generic way of describing symmetry that works kind of like the most abstract level, but in terms of layman's terms as well. And kind of like what we saw earlier, these basic transformations, the idea of symmetry extended, basically you have the original shape. Okay, that you're translating it. Okay, that's still the same shape. Now you translate it and scale it. And you can rotate it, you can reflect it, but you can see it's still the same shape. You've transformed it with these basic affine transformations, but what stays invariant is basically, okay, the angles between the lines and the relative size of the lines in relation to one another. That is the invariant aspect. So even when you scale it and you reflect it, that invariant description stays the same. Now, okay, the question is there an invariant aspect that pervades the entire brain, that pervades all the brain, everything in it, that pervades the genome, pervades all the aspects of the genome, what it does, ontogenesis, all the structures of the body it creates? Is there a single invariant aspect that pervades all of it? And the answer is yes. And once you understand this invariant aspect, then basically you have the means to create this unified theory of life and intelligence. You also have the means to create artificial intelligence using this abstract invariant aspect. And what is that invariant aspect? It is basically our binary tree. It's our binary branch. Okay, so I'll basically go on through this. I go through this in the Fractal Brain book in depth, but I've done it in previous talks this year. But I'm just going to go through it quickly, because for what we need to explain to do with what's called positional encoding and reference frames and in artificial intelligence, machine learning, this is important. Okay, so basically it's to do with spatial mapping and how we represent time. So this is to do with what's known as egocentric spatial mapping. This is really important. Egocentric. There's egocentric and allocentric. Okay, egocentric means, okay, I'm sat or stood in the same spot in reality, and basically, and then I'm looking around that same spot. Okay, allocentric means what you see on your GPS is basically your position on a map. Is basically you kind of like, you know, you're moving around space. But when you're in a certain point in space, you can look around different parts. And that's egocentric. So I'm sat in this chair, this swivel chair, and I can basically point to things. That's my egocentric frame of reference. Okay. Now, sometimes we learn how things work when they go wrong. And there's this condition called hemispheric neglect, and it involves a kind of like lesions. It's a part of the brain called the right parietal cortex. You literally lose half your world. Okay, you lose half your world. So a kind of hemi-neglect patient asked to draw a house can only draw half of it. Asked to draw a clock, can they put the numbers on one side? Okay, he's asked to walk down the street where he lives. Okay, and then basically he's asked what's on the right-hand side. He can recall perfectly what's on the right-hand side, but he can't recall what's on the left-hand side. He's lost half the world. He's asked to imagine walking to the end of the street and turning round. Now he can recall the things on the other side of the street. Now he's lost what he could record earlier. So, and asked to read a word, you can only read one side of the word. It's almost like you're recursively subdividing your egocentric space. And hemispheric neglect kind of patient asked to eat a plate of food. Okay, we go through in sequence. Okay, here's the plate of food. He starts eating, and when he eats half the plate of food, he stops eating. You can't see the other half of the plate. You turn the plate round, he starts eating again, and then he stops. You turn it around, he starts eating, and then again recursively subdividing. Okay, so we think it's a kind of binary structure underlying egocentric mapping. Now, what's called allocentric mapping is basically like your GPS. Now, won a Nobel Prize in 2014, Edvard Moser and Britt Moser, his former wife. They found what's called grid cells in the hippocampus. Now, grid cells show that basically as you walk around a room, basically cells will fire in your hippocampus, and they'll fire when you're in the center of a hexagonal grid that your brain superimposes on the floor space. So as you walk around the room, as you get to the center of these hexagons, these place cells will fire these grid cells, they're called. Now, okay, this is equilateral triangles, but equilateral triangles also the center of hexagons. Okay, so this lady here, okay, basically is standing in different grid sizes. what they found was basically these grids come in different sizes, okay, and the scaling factor between the different sizes is actually 1.42. Now, the critical thing there is that the 1.42 is roughly the square root of 2. So you times by 1.42 twice, you double basically, and or you divide it and then you halve. So again, you see this kind of doubling, halving kind of pattern in allocentric mapping as well, along with egocentric mapping. Okay, we've spent a long time talking about these things, but basically this doubling pattern is absolutely universal. It's in basically spatial frequency processing in the visual cortex. It's to do with brain waves as well, absolutely universal. Now, to represent time, okay, back to Jiri's question, okay, yes, these brain waves, they split up time in a seemingly discrete manner. But we've already, explained with the what's called theta phase shifting with place cells. That yes, it's discrete, but there's also, you can also represent the continuous, and we can also use our binary tree language tend to represent that phase shift as we showed earlier. Okay, now okay, for universal invariant aspects, what we know is that basically the main brain waves, they come in powers of 2. So gamma waves are roughly 40 hertz, beta waves roughly 20 hertz, alpha waves 10 hertz, theta waves 5 to 6 hertz. Now, on an EEG, when you put surface electrodes on, then the brain waves are all over the place. It's a complete mess. But when you have under the surface, when you actually open up the person's head and actually put electrodes in, they have a very precise kind of like phase precise behavior. So gamma wave is exactly 40 hertz because it's modulated by an inhibitory neuron. So the neuron fires, okay, then the inhibitory neuron stops it from firing. But that inhibitory neuron has a refractory period, a recovery period of about 25 milliseconds. So which is roughly a phase of the complete wave of gamma wave. So then it fires again. So it produces a very precise 40 hertz signal, and similar mechanisms for beta and alpha waves. So basically it's very, very kind of like precise, and it comes in powers of 2. And this is to do with time, okay? We can go on. I mean, basically, we've covered this in the book, and we go into details. It's absolutely ubiquitous, but for our purposes, for explaining the next question in artificial intelligence, we just deal with spatial and temporal mapping. So, okay, binary trees and language, binary trees and syllables processing, phoneme processing to do with brainwaves, music, powers. Okay, we can go on. I mean, basically, mitosis powers of 2, progenitor fields, it goes on and on. Okay, for spatial mapping, okay, the way the genome represents space along the axis of a fruit fly is again a binary structure. So this is fascinating, isn't it? So basically, over time, you see where the cursor is. Over time, this is a kind of fruit fly developing over time, and this is the long axis of its body. And over time, what happens is that the genome lays down these chemical markers. Okay, but these chemical markers, you see that they lay down a pattern, and it's basically a doubling pattern. And you can actually draw a binary tree through that pattern. What it means is that all these chemicals give you a binary combinatorial code that exactly specifies a point along the long axis of the fruit fly, which is exactly like your allocentric grid cells, which is exactly like your egocentric mapping, this subdividing into 2. So it's fascinating that the genome is actually representing space in the same way your brain is doing allocentric, egocentric spatial mapping. Okay, look, we can really talk at length to explain that this binary pattern is absolutely ubiquitous. I mean, neurons themselves are binary trees. You obviously use binary trees to describe genes and genomes because they're like, lists, aren't they? But we will move on because we've dealt with this in previous talks, and you can read about it in the Fractal Brain book. Okay, what this allows us to do, basically, what we've talked about, allows us to resolve a very important issue back to machine learning and artificial intelligence. So we skip loads of explanation there in order to arrive at answers to questions 7 and 8. Okay, so back to machine learning and artificial intelligence now. Okay. A critical question is to do with reference frames and what's called positional encoding. So basically, okay, you got these deep convolutional neural networks, but there's something wrong with what they're doing because you can't actually locate different parts of the image. There's no kind of reference frame to actually subdivide different parts of your input data. So Peter Norvig, who wrote that great big book on artificial intelligence earlier, he put it very well. I mean, he was the head honcho, overall head of technology at Google until he retired. He was a former Stanford professor who taught the Google founders. Anyway, he put it very well that backpropagation neural networks, deep convolutional neural networks, suffer from the problem that, quote, everything is everywhere. Change anything, you change everything. So it's all intermingled. There's no way of referencing different parts of the image, you see. And positional encoding has become a very important topic because of this thing called transformers, okay, paying attention to different aspects of strings and sentences. The problem is basically, how do you represent space and time in artificial intelligence, machine learning? We have the answer right from neuroscience. It's using binary trees to subdivide space and time. So we know this is how the brain works from what we've described. And it's just a perfect way of doing it in artificial intelligence. And if it's being used in computer science anyway, for video compression and for, you know, wavelet compression and representing lists and lisps, then it's actually the best way to go. This is a bit specialized in this thing called transformer technology, which is the latest and greatest tech in the machine learning world. You know, it's GPT-3, you might have heard of that. There's the GPT-4 coming, okay. Now, there's a way of representing positional encoding. It uses sine waves. It's grotesque. It's incredibly clumsy. There's a far, far easier way of doing it. You do it like the brain does it. You do it like the genome does it, you see. We know the brain works. We know the brain does process space and time. So there's your answer. There's actually papers which are suggesting this is the case anyway, because, okay, this is a little bit specialized. There's this idea that it's true, basically, that transformers are essentially what's called graph neural networks, okay? But then you can represent graphs as binary trees, okay? You know, graphs are basically different nodes, interconnected nodes, but then all those nodes can be seen as end nodes of a binary tree, in which case, if transformers are graph neural networks, then those graph neural networks can easily be represented as binary trees. So it's almost there. It's almost, you can actually slot in how the brain does it directly into how transformers do it, and do away with all this kind of clumsy sine wave stuff that they're actually using now. Okay, now, so that's the answer to how we represent reference frames in positional coding. We use binary spatial codings with this shift phase factor that can do the continuous. Now, Symmetry Ai and Analogy has become very trendy just in the past year. There's people like Douglas Hofstadter who have been saying it for years, that analogizing is really important. Of course, you know, you can't have brittle analogies. Analogy implies symmetry, it implies something invariant. If two things are completely, there's no invariant aspect between two things. It's senseless to draw an analogy between two. So analogy implies symmetry, and symmetry, you know, leads to the idea of possible analogy. It's become very trendy because the DeepMind's AlphaFold uses notions of symmetry to get its performances, basically. So basically, the most recent breakthroughs of DeepMind derived from a work called Imperial College professor called Michael Bronstein, who came up with a recent paper on symmetry in deep learning. So it's become a very hot topic. What we propose is basically that what's called symmetry priors, or the idea that the world is full of symmetry, it's full of recursively nested pattern, it's full of fractals, basically. The reason why we can actually predict things is because there's temporal invariance, things stay the same, and basically the world, our reality, is just packed with, you know, recurring pattern or invariant pattern. That's the reason why we can make sense of the world. So that's the notion of symmetry prior. Now, there's a notion called inductive priors, and that is that we exploit these symmetry priors in reality by using inductive priors. Now, one example is convolutional neural networks, which have this kind of slide factor all built in, like we talked about earlier. So it's kind of exploiting translational symmetry. And that's what it's doing. Now, we suggest that basically it's not about, you know, kind of like using this inductive prior or that inductive prior and selecting into your neural network, into your machine learning. What we're suggesting, and what we kind of like were saying earlier on, you don't kind of bake in the inductive priors into your kind of artificial intelligence architectures. What you do, the trick, and what we've done earlier, you actually bake in all the inductive priors into the actual language which describes all your different, neural network, machine learning, artificial intelligence architectures. So the inductive priors actually baked into the language which describes the artificial intelligence. Do you see what I mean? And then the trick then is to learn the inductive priors you want. So we kind of take the ideas of symmetry priors and inductive priors to the max, and we merge it with a fully symmetry, self-symmetry architecture of the brain, and derive fully self-symmetrical fractal artificial intelligence from this fractal brain theory. So essentially, what's happening in this, these questions to do with symmetry is convergent with the idea of a fractal symmetry, self-symmetry brain architecture. So the answer is right there in the idea that we showed earlier, basically that the entire brain is fully symmetrical and self-similar. So we just explained, because it takes some time to go through the entire brain, we did it for a pyramidal cell and the entire brain. So we with about 2 hours, we can do basically for all the rest of the brain. So that is essentially the answer to the this hot topic of symmetry analogy. That's very well. It kind of takes the current research to its logical conclusion. Okay, that's what I'm saying. Now, okay, we just work through the rest of these big issues in artificial intelligence, machine learning. Now, a major issue is the next step, according to many of the leading lights, is generative predictive AI or causal AI. So Geoffrey Hinton quotes, okay, generative models, that's what I really believe in. Ultimately, I'm completely convinced that generative models would be better. Jan LeCun again, a learning predictive world model is what we're missing today, and in my opinion, is the biggest obstacle to significant progress in AI. Demis Hassabis of DeepMind, the hardest challenge in AI research to build an agent that can plan hierarchically, is truly creative and can generate solutions. And Judah Pearl, a kind of major probability theory Bayesian theorist, we must invoke causal models, associations not enough. Now, okay, the idea of generative, predictive, and causal, they're not mutually exclusive. Because if I generate a pattern forwards in time, like I do with my kind of stratum loop Lindemeyer system generating a pattern forwards in time, okay, if I basically that is like a prediction, isn't it? So if I generate a pattern forwards in time, that is like a prediction. Now, if my prediction matches with reality, there's a possibility I've actually learned a causal relationship, isn't that so isn't it fairly clear that basically generative, predictive, and causal, they're actually interrelated concepts? So we think that basically there is a universal generative, predictive, causal algorithm that covers not just the brain, but the genome as well. Now, this kind of speculation in artificial intelligence, machine learning by these leading lights, they converge with a very big idea in neuroscience. Okay, the idea is, it's called predictive coding theory. The idea is also called analysis by synthesis in the States. And a guy working in London called Carl Friston calls it active inference. And we think this idea is absolutely right. We think this idea is very old. In fact, I mean, the era of psychophysics talked about this idea 100 years ago. In fact, back to the talk 2 weeks ago, the Corpus Hermeticum in chapter 13 talks about the complete intertwining of sensing and understanding. You can't sense without understanding, and vice versa. You can't understand without sensing. What this idea is saying, basically, when you perceive things, you don't just passively infer what's coming through your senses, what you're perceiving. You actively generate a prediction from inside, then you match what you perceive with your prediction. So that's predictive coding theory. So okay, a good example of this in action. Okay, basically you have a suitcase, you know it weighs a certain amount. And basically, as you reach for the suitcase, if you know how much it weighs roughly, because maybe you packed it or you know roughly, as you reach for the suitcase, you anticipate, your muscles actually anticipate, you get ready to take the weight. So you're actually predicting. Now, if you didn't have that prediction, it'd be hopeless. And if you're, if you misjudge, if you expected a heavy suitcase that contains nothing, well, you pull it up. Or you expected a very light suitcase and it contains a ton of bricks. And, Did you see that? That's an example of predictive coding at work. But it's a very general thing because it's happening all the time. Everything you perceive, everything you hear, everything you touch involves predictive coding. We think this idea is absolutely right. It's old, but it's now absolutely in trend now. Okay, so where does biology come into this? Okay, biology is correct in this respect, and it converges with what these people are anticipating in the world of artificial intelligence, machine learning. What we propose and what the fractal brain theory is saying is that there is a single generative algorithm. Now, that sounds outlandish, and it kind of converges with notions of a master algorithm, a single algorithm that can capture all the separate algorithms. Let's go through this quickly, because we can do it because we've explained this new generation of how axons and dendrites actually work. Okay, so basically, the fundamental, if there's a fundamental structure of trees, what goes with it is a fundamental algorithm. That algorithm is to do with evolution, okay, but it also captures all the other generative algorithms. Now, people studying evolution in, say, the Santa Fe Institute, kind of complexity theorists, they try to abstract evolution in a kind of like abstract mathematical language. What they describe evolution as, it's 3 steps. It's differentiate, select, amplify. So you have a species, you differentiate. This is a kind of a descent with variation. You select those individuals that are most fit. Then you amplify those individuals. And you do the same with entire species. So basically, the species differentiate into different species. Some are selected, some are amplified, and some go extinct. What we have then is an evolutionary tree of descent, like a tree exploring into the space of possibilities. Some branches are chopped off, and some branches are reinforced. Now the second point in the diagram, okay, ontogenesis is also differentiate, select, amplify. Because you differentiate into space, your mitosis, you're generating cells, you're generating different parts of your body. Some of those cells will become programmed to die, some will become reinforced. Some parts of your body will get bone and blood vessels and skin and become reinforced. And some parts of your body, as it develops, will wither away. But even ontogenesis is, again, differentiate, select, amplify. You're differentiating, selecting, and amplifying certain parts over other parts. Now, okay, back to the first part of the talk. The way axons and dendrites and synapses working, back to our Lindenmayer diffusion limited aggregate, we're also differentiating the space. We're now, with this new dynamic axon, do you see? We can interpret axons, the way they work, also in terms of differentiate, select, amplify. And what you're amplifying is those axons which then converge with dendrites, and then they form synapses, and then the synapses is literally physically amplified. And with what we described earlier with the behavior and thought reinforcement learning circuit, again, you're kind of like Lindenmayer system, kind of projecting behaviors forwards in time with your stratum, but now you're amplifying things, rewarding things with your dopamine circuit. You're literally physically reinforcing certain kind of chains of behavior chained by your stratum with dopamine, the pathway of addiction. And onto point 5, when we understand that evolution is happening at the whole brain level, that your creativity and your innovation, generating new thoughts and behaviors, is like evolution, that will also be a process of differentiating, selecting, and amplifying. What it means is that there is a single differentiate, select, amplify algorithm that can start right from a fertilized egg, ontogenesis, to the formation of neurons, to the linking up of neurons, to the chaining of behaviors in time, to the evolution of those complex thoughts and behavior. It means that you can capture everything in this diagram with a single algorithm. And the algorithm is like a tree structure, differentiating, selecting, and amplifying. And what we think with this new way of looking at neurons, which is essentially differentiate, select, amplify, we can capture essentially all kind of like, or most of the kind of like algorithms in artificial intelligence, machine learning, apart from backpropagation. So here, look, in this diagram here, we show basically that most of artificial intelligence, machine learning, is essentially discrete stochastic search and Monte Carlo-esque kind of processing. Now, what this means is basically discrete stochastic search is an example of differentiate, select, amplify, But what you're doing is you're differentiating in a stochastic way, like Monte Carlo, like throwing dice. But that's exactly how evolution works. So what it means is basically everything in this diagram, what's called neuro-architecture search or neuroevolution, generating neural networks. Okay, this is mainstream artificial intelligence, machine learning. What's called the lottery ticket hypothesis, actually, that the neural network, your backpropagation neural network, will converge to certain solutions if the initial configuration of weights is correct. It's like a lottery ticket. So basically, depending on the random configuration of weights, your neural network will work well or not. Okay, we think that basically the generator of the lottery tickets is also the process of differentiate, select, amplify. And then onto this new generation of neural networks, you know, based on a new pyramidal neuron understanding, which is also discrete stochastic search. Now, the interesting thing is we're trying to replace backpropagation neural networks, but in all applications and implementations of backpropagation, what's used is what's called stochastic gradient descent. So you have this continuous gradient descent, but you add this kind of like stochastic Monte Carlo factor effectively. What we're saying is you're already using the stochastic element. What you need to do is just get rid of the gradient descent element, and you do it all using stochastic search. And okay, we've done reinforcement learning as a kind of differentiate, select, amplify, and evolution of complex patterns. It means that these ideas in artificial intelligence are already convergent upon the things we've been talking about anyway. Okay, so that is the generative kind of like causal predictive aspect captured by a single algorithm. Okay, I'm going to skip through this because we're kind of running out of time. I just want to cover the last section. Okay, the other aspects want to cover just fairly quickly in the next kind of 20 minutes to 25 minutes because we've gone on a bit. Okay, look, we just go through these questions now. Okay, so the other big issues in AI and machine learning. Okay, why has it been so hard to create true AI and explain how the brain and mind works? We kind of touched upon this in the question earlier on. It's because of specialization. It's because the fact that we think the reason why we've not arrived at true AI and understanding of how the brain works is because of specialization, because how academia and corporate labs work. They work in a way of demarcation and basically, you know, putting yourself into a box. We think that the problem of creating true AI and understanding the human brain and mind is non-decomposable. Now, okay, leading light again, Jeffrey Hinton, he says, okay, so he says, obviously, quote, I'd like to have one solution to everything. That's what everybody wants. It's just you have to be more realistic and get parts of this. You can't get the whole thing at once. What we think is that the reason why the mainstream academic labs and the corporate labs have not understood AI or the brain is because we believe you can only get the whole thing at once. Now, this idea of decomposing a problem into separate parts and having different teams solve the problems and then kind of unifying the partial solutions to get the whole answer, it just doesn't work for the brain. We know it doesn't work because we've gone through the same process for decades, decades of artificial intelligence research, decades of theorizing about the brain, but no one's come up with the answer. We think it's because you have to take everything at once and consider it in a completely holistic way. We think that's where the answer lies. Okay, so I write about this in the Fractal Brain Theory book. I call it the Gordian knot of artificial intelligence. This is a diagram from the book. It basically shows the intertwining of all the separate puzzle pieces and show how they're interlinked. Now, we won't go through the details of the Gordian knot for lack of time, but what we will do is show how the idea of a Gordian knot, how the intertwining of all the puzzle pieces allows us to solve and see why all these desired learning aspects that artificial intelligence and machine learning needs to be, that it doesn't do, will show how all these different aspects are basically completely intertwined. And once you see they're completely intertwined, you see the path to the solution. And once you see how all the separate factors, the answer comes from biology, then it's a matter of basically adding up all the separate solutions from biology take them together, and there's your solution to all the separate puzzles. Okay, so learning needs to be transfer. You need to be able to transfer previous experience to new experience. Okay, so it needs to be zero few shot. Okay, existing machine learning, you learn stuff in terms of tens of thousands, hundreds of thousands of iterations. Andrew Ng, who is a Stanford former head of the Stanford AI lab, he said, you don't teach your baby the concept of a cup by showing your baby 10,000 cups, do you? Okay, that's a good point, isn't it? We learn in what's called poverty of the stimulus in very few shots. Learning needs to be on the fly. Basically, existing AI, there's a kind of learning mode where basically you're like a zombie. You take these tens of thousands of iterations and you basically in a passive mode. And you don't interpret anything. Basically, you just let the learning wash over you, and you kind of forget all you learned previously. And then you have a kind of inference mode where you basically do all the pattern recognition, but you don't learn anything. The trick is basically you need to merge both. You need to make learning on the fly. We covered compositional and incremental learning earlier on. We showed the solution in biology and explained what they were. Unsupervised learning is basically what machine learning does. You have labels, you just basically match input to labels basically, but things in real world don't come labeled. We talked about reference frames and positional encoding earlier on. We talked about symmetry and inductive priors. Now we think that all these ingredients have to work together in a holistic way to solve each of the separate puzzles, okay? So let me go through this. It's because of this. The generative predictive AI aspect is completely right, as we talked about earlier. We basically believe that this predictive coding theory, this analysis by synthesis is absolutely right. And what this means is basically, as we interpret the world, we're actively projecting a prediction. Now, this necessarily involves transfer and analogizing, because basically we're always matching what was our current situation to the best match we have in our minds. So we're always trying to predict the world. So necessarily involves transfer and analogizing, which necessarily involves, as we talked about earlier, symmetry. So we can't form analogizing without symmetries in the world. We can't do it without temporal invariance. We can't transfer from the past to the future if the laws of physics change in the future. And in turn, okay, if we make a perfect prediction, if our predictive coding perfectly matches with what we're sensing, then that is effectively zero-shot learning. There's nothing to learn. If basically your route to work is the same as what was every day for the past 10 years, it was completely boring, basically there's nothing to learn. You have to learn every time you go to work, the route to work again. It's the same thing. It's a zero-shot learning. Basically, you knew it already. Now, we believe that few-shot learning is to do with, we learn by learning the deviation from expectation. So if predictive coding, we're forming an expectation, then what we're learning is the deviation from that expectation, which means that learning is necessarily on the fly, because it means that we have to predict. So we have to infer in order to learn. So therefore, learning and inference is necessarily on the fly. Okay. And if there is a deviation from expectation, then what we do is we composite, okay, point 4, compositional learning, we composite that deviation to what we predict, our predicting mechanism. Now we add the deviation incrementally, incremental learning, but this requires reference frames and positional encoding. Now look, suppose I see someone, I thought it was my brother. I was walking down the street and I thought, oh gosh, I was predicting that was my brother. I was also going to say, hello, brother, but it wasn't. It was someone looked like my brother, but he had a hooked nose, and he had his eye was slightly crooked, and he had an eye patch on his eye. Okay, what it means basically, what I do is I don't learn a kind of like a completely new instance, 10,000 iterations of basically learning this new guy. I basically take this guy looked like my brother, he walked like my brother, basically the same height and stuff, but he had a hooked nose. So you position the deviation, his nose, and something to do with his eye, you position that. Okay, it means that you need reference frames and positional encoding, but you also need symmetry, because you need basically to represent the deviation. You might need to rotate. He had an eye, but it was slightly kind of rotated slightly. Or he had a mole, but it was kind of positioned over there. It was slightly larger than my brother's mole. But did you see? that all these separate aspects are completely interlinked. There is no, to solve these separate problems, there's no forming a team to solve the problem of transfer learning, a team to solve zero-shot learning, a separate team to solve on-the-fly learning, etc. Because all the separate pieces of the puzzle are completely interlinked. And you can only create AI and machine learning that does all these separate aspects by integrating all these separate aspects to work together at once. So that's one example of the application of the Gordian knot aspect to really solving these really central problems in machine learning today. Okay, so I'll skip over 5 because that takes some explaining. Okay, the issue of energy efficiency, which is very another Achilles heel of backpropagation and deep learning neural networks, that the energy usage for all these GPT-2s, GPT-3s is going off the scale. It's really like, talking like tens, hundreds of millions of dollars of electricity and compute power to train one cycle of GPT-3. So it's not sustainable, and GPT-4 is anticipating it need this new kind of 3-brass wafer scale integration hardware in order to power it. Anyway, it's really unsustainable, and basically the other problem is that basically we want machine learning, we want kind of artificial intelligence to work on small devices, IoT, but also smartphones, and also kind of very small machines on the edge, what's called tiny machine learning. Okay, so by doing one-shot and a few-shot learning, automatically, by not doing tens of thousands of iterations, we've gone a long way to solving the energy issue. And also the fact that one of the major problems with kind of machine learning, deep learning neural nets, is basically you're shuttling huge amounts of data, these massive data arrays, kind of huge matrices and vectors, many hundreds of gigabytes, and you're shuttling it into memory, into your GPUs, and then you're doing all these dot product multiplications, shifting a huge amount of memory. Now, interesting fact is basically the amount of energy it takes to do the floating point calculation, okay, in a kind of floating point register, is actually 1% of the energy it takes to move the data that you use for the multiplication from your DRAM to your SRAM up your memory cache around the GPU, in order to do. So 99% of all the energy is actually used to move data from memory to the actual registers. Now, when we use this kind of new technique of actually using this kind of like dendritic patches and kind of like selective usage of tiny fractions of the synapses in order to learn something, it means that we take a tiny proportion of the data. We take a tiny fraction of a percent of the data that would be shuttled using backpropagation techniques. So it's highly energy efficient. Anyway, so what we talked about earlier with to do with few-shot learning, and also the kind of like dendritic patches, goes a long way to making things much more energy efficient. We've kind of done the neuro-algorithmic already, because we basically talked about the kind of neuro-oscillatory loops. One of the simplest programs I ever wrote, one of the first programs I wrote as a kind of like 11, 12-year-old is basically a basic program, 10, print something, 20, go to 10. And that's a simple program, that's an algorithm. But oscillating neurons are essentially doing the algorithm. So in a very simple way, even a neuron does something algorithmic. Now, we can cover this quite quickly, because the conditional expressions from the neuro-symbolic Boolean, that in computer programming, basically you have conditionals, basically, if something, do this, while this, do that. But we showed earlier how dendrites in these tiny patches do essentially Boolean processing. And we showed earlier how the basal ganglia, how the stratum, these striosomes and matrices do essentially, while the dopamine flows, do a loop, while some condition, repeat until, etc. Now, in terms of memory store, okay, basically we can store things using our egocentric maps and our allocentric maps. So memory store is like, memory store in a computer is like different places. They're like little boxes you put bits of data in. So the idea of neuro-algorithmic memory is basically you use the spatial mapping we talked about earlier in order to store things. Okay, so this is quite a hot topic, because Edvard Moser, who did egocentric stuff, he's basically releasing papers and saying that cognition is using egocentric mapping or an allocentric mapping in order to represent and store information. So you're kind of taking the way we represent physical space and using that to store memory items. The other thing which we need finally to address is basically recursive processing, which is really important for computer algorithms. So this is the final part of the talk, and it's really okay. The final part of the talk, okay, that does a bit kind of maybe esoteric, but the final part of the talk will discuss what's uniquely human, because we basically want to just in the final part talk about what is it about the human brain which is uniquely human that we need to basically implement to create human level AI. Okay, so that also allows us to do fully recursive processing in the brain. Okay, so now we're going to basically in this last section just discuss this critical part of the brain. It's called the polar frontal cortex, and there's a part of it which is absolutely uniquely human. Now in this diagram, you see a kind of like the polar frontal cortex. This is a monkey brain. So it's basically the front part of your brain here that's called the polar frontal cortex. And there's a part of it in the human brain which is absolutely unique. It's not found in any other animal, any other ape, any other kind of higher monkey or whatever. And what does this part of the brain do? Okay, there's different factors contributing to human intelligence, why we're smarter than animals, but the real important factor is this polar frontal cortex. I'll just skim over this diagram for lack of time. Okay, so this polar frontal cortex, okay, it's very, very special because in humans, it's larger, absolutely and relatively. So in this diagram here, we can see that the polar frontal cortex, you see it's much larger. On the left-hand side, there's your human polar frontal cortex in orange, kind of flattened out, and that's a monkey brain. You see the orange part is very small in terms of absolute size. It's much, much bigger in a human brain, but also in terms of relative size. Can you see relative to the rest of this part of the brain in a human, it's far, far bigger. The other thing about the human polar frontal cortex is that, okay, it has the neurons with the highest synaptic density. So if these pyramidal neurons are performing these kind of like dendritic patch operations, then your polar frontal cortex neurons has the highest density of these dendritic patches and kind of processing elements. Now, unusually, the polar frontal cortex is not connected to sensory inputs. Okay, it's not connected to the sensory parts. It's unique. It's it's like it has an overview. It kind of exists at the kind of like the apex of all the hierarchies. So you have a speech hierarchy, you have a spatial processing hierarchy, you have all these different hierarchies in the brain. It kind of is like an extra apex over all the separate hierarchies in the brain. Now, what also makes it really special is its connections to key parts of the brain. So this polar frontal cortex is connected specifically to very important parts of the brain. This scan was from a research paper in 2015, which really nailed the issue of what's unique in the brain, because it really did show using DTI scans that really this part of the brain is connected to other parts of the brain like no other part of the brain in any other animal. Now, to what is this part of the brain connected to? Okay, so this is how it connects. So this polar frontal cortex, it connects to these very special structures. Okay, in a human brain, can you see it's much more extensively connected to the back part. Now, the polar frontal cortex, when I'm shaking my cursor, okay, it goes back via this thing called a cingulum bundle, and it projects heavily to this part of the brain called the precuneus. Okay, the precuneus, this part of the brain, is to do with the egocentric map we talked about earlier. So you point and reach different parts of the visual, field, like a blackboard kind of representation of space. It's handled by this precuneus, this kind of first person experience kind of thing, this egocentric map. As we loop back, okay, it also connects to areas 30, which is called the retrosplenial cortex. It is a part of the brain very important for memory access, for recalling memories. And it loops right through to the hippocampus, entorhinal cortex, this what's called medial temporal lobe, to do with memory formation. So the parts of the brain to do with spatial mapping and to do with kind of memory recall and memory formation is exactly what this polar frontal cortex is connected to. And it's also connected to the apex of all these different hierarchies. It's a very, very important part of the brain, really, really important. That's another scan of basically the polar frontal cortex. You see, that's the precuneus to do with first person kind of, experience, kind of first person views of the world. You've got an egocentric view. Now we ask, okay, that's another diagram from monkey brain. In the human brain, it's more extensive, but that's the retrosplenial cortex again. But the connections to the amygdala, which is to do with emotional processing, but also heavily in the human brain, the polar frontal cortex is connected to this parts, not so much in monkey brain. This is to do with speech processing and audio processing. And this part here, very heavily connected in the human polar frontal cortex, it's called a semantic hub. It's basically where the hub of meaning is happening in your brain. Okay, so what's the polar frontal cortex doing that's so unique to human cognition? I'll tell you what's doing. It's doing this, and we need to replicate it in a computer to create true human level artificial intelligence. Now, the standard view is that it's doing multitasking and recursive subtasking. This is the standard view that is generally accepted. So this is a meta study from over 100 functional MRI scanning studies. But can you see, okay, mentalizing is basically understanding the minds of other people, and that's memory access. But can you see the green part, very pole? What these scans are showing is handling multitasking. It means when you have to handle multitasking, the polar frontal cortex is absolutely essential. Okay, now how does the brain handle multitasking and also what's called recursive subtasking? Now, recursive subtasking is, imagine I'm watching a video, okay? Then suddenly, as I'm watching the video, I get hungry. And then basically, I need to pause the video. Okay, there's nothing in the fridge. I've got to contrive the example. I need to go to the shop. So I need to get in the car. I've got no money. So I need to, a subtask. I need to go to a cash machine, get the money. A subtask, each number of pressing is a subtask. Then I get back in the car, and then I get back to the subtask of buying food from the shop. And then I buy the food, I eat the food, subtask done, I go back to the video, back home, and I start watching the video again. See, that's cognitive subtasking. But how do I do that? I suggest that how we do it is exactly how it's analogous to how a computer does it. Now, how a computer does multitasking and recursive subtasking is that a computer, okay, what it does, it takes a snapshot of the system state, and then it puts the system state on what's called a stack. It's a memory store. So I suggest as we multitask, we have to, okay, I'm doing one task. To multitask, I need to take a snapshot of what I'm doing, put it on my memory store, and I can because the polar frontal cortex is connected to all the right areas. I do the other task. When I finish the other task, I come back to the first task. I take that off the memory stack, and I'm back doing the original task. It's multitasking. Okay. Now, recursive subtasking, it just means I keep pushing those subtasks onto the stack. So the task of watching a video, I stop watching the video to get the food. I take a snapshot of myself watching a video, put it on the stack. I get the food and I come back and I load when I get back home, where I was watching the video back into my mind. Okay, now this is where it gets interesting. Okay, what if, okay, I take a snapshot of my brain and put it on a stack. But now what I'm doing now is not to go into a subtask. The subtask now is to look at what's on the stack. Okay, what it means is this. It means I can think about something. I can take a snapshot of myself thinking about something, put it on a stack. But now I can think about myself thinking about something. But then I can take a snapshot of that. Now means I can now think about myself thinking about something. You see, it's a really important facility that you have from your introspection. Years ago, this book called Gödel, Escher, and Bach by Douglas Hofstadter, he wrote a book and he basically said this is something that computers and artificial intelligence can't do. He called it jumping out of the system. But you see, with this very amazing system in the polar frontal cortex, by taking a snapshot of myself, I'm not physically jumping out myself, but by taking a snapshot, and put it on a stack, as if I'm jumping out of myself to analyze myself recursively, thinking about myself, etc., and so on. Okay, so it's really, really important, and we can actually program this into this next generation of artificial intelligence based on brain architecture. It's called metacognition. It's called introspection. That's something we do all the time. And it requires, I believe, the polar frontal cortex. What's really important about human behavior is what's called a social brain and mentalizing, basically. Now, by taking a snapshot of myself, I can also then think about what other people might think of that snapshot. And then I can take a snapshot of that. Then I can think about myself. Then what do I think of that person thinking that about me, etc. See, I can actually socialize. I have not just introspect. I can actually go into other people's brains now and actually analyze social situations. And not just that, but I mean, what we talked about earlier about representing kind of memories using egocentric maps. It means that basically, if I have a kind of blackboard, what's called a kind of like a visual spatial sketchpad. It's like back to algorithmics. It's like how we do memory. We have an egocentric blackboard in which we can place different things. Okay, we can visualize it. Now, what if I can recursively take a snapshot of that blackboard? Okay, put it on a stack, then have another blackboard and put that sub blackboard into my other blackboard. It means I can have an overview of a piece of music and I can zoom in on different parts and then zoom in on it. It means I can basically use the stack facility combined with this egocentric map, because I can reference different parts of the egocentric map and I can place different submaps or sub blackboards within that blackboard. It means I can create recursively spatial structures of arbitrary infinite complexity. I can do the same with language. I can basically take sentences. I can recursively nest sentences within sentences. I can do it with any kind of modality. I can basically recursively nest structures of arbitrary infinite complexity. So I suggest this is the thing which really makes humans intelligent way above and beyond any of the smartest chimpanzees, which means bonobo chimpanzee. And I suggest by modeling exactly the connections of the polar frontal cortex and this uniquely human part, we can completely recreate this in a machine. So, okay, that is really, I guess, the cherry on the cake. Basically, we propose to, use these ideas to create human-level AI and beyond. So, okay, this is really like a skimming stone talk. This is really like, we covered a lot of ground in a kind of skimming stone way. It's 2 hours, as a lot of material covered in 2 hours. But I hope I've given you a kind of a new perspective on artificial intelligence, machine learning. And with the human level AI stuff and the polar frontal cortex, I hope I've given you at least a glimpse into the feasibility of reproducing all these kind of metacognition aspects of human intelligence, these introspective, kind of really powerful recursive aspects of the human mind. So basically, what it means is that you take all these factors I've described tonight that are backed up, the answers all come from biology. You bring them all together in a holistic way. You combine the uniquely human stuff, and basically that is the blueprint for creating true human level artificial intelligence. Using the ideas of symmetry and this new discrete binary tree, quad tree, shifting squares language, combined with everything you heard tonight. So I guess I'll stop it there. That is basically that's basically it. And what it involves is basically what I'm doing now is coding all these ideas, creating the algorithm to implement them, and it leads to what I describe in both books I've written, the Fractal Brain Theory book and the Quest book. It leads to the creation of what I call the startup at the end of time. And I believe this startup at the end of time is basically what will create true artificial intelligence. And it links up with the talk 2 weeks ago, because I think it's the means really to push the ideas we talked about 2 weeks ago into the mainstream. So it's one interconnected message. So yes, this is all artificial intelligence and stuff, but I think there's a wider game. It's not to become the next Elon Musk. The startup at the end of time exists to create true artificial intelligence in order to, it's like a thin diamond coated edge of a very big wedge. And that wedge is an entire 21st century worldview. And that's basically the subject of all the other talks I've been giving over the past 10 years. Anyway, I guess we'll leave it at that. I guess that's roughly over 2 hours. That kind of overran slightly. I skipped over loads of material. There's obviously far more material than I thought I actually prepared, because a lot of this is new stuff. So I mean, this is probably to do it properly, we are actually 2 talks. But what's going to happen in the future is basically there's going to be lots of short videos. I'm going to segment all this stuff. I mean, there's the 2 AI talks I did in the spring, and a lot of that is not actually contained in this talk. So it's probably about 6 hours worth of AI material. There's all actually one interlinked great big talk. So what I'm going to do is systematically re-go over it all again and sequence it in nice kind of 10-minute, 15-minute chunks and do it in front of a green screen. So that's what we're doing in the new year. So anyway, that's it, folks. You know, amazing patience. And if you've got any questions, I'll be here for at least, well, as long as it takes. I mean, any questions? Well, I drink a bit of coffee and...
I've got more of just an observation.
Yeah.
All right. So you said that one of the keys to creating true AI is this regenerative algorithm. It's like a single regenerative algorithm. And given like the nature of just how like quickly we've seen the world change, you know, even over the past year or two, and just, you know, how the nature of things are going, you know, when a new fad or you know, internet meme comes up or something, it gets spread, everything just gets spread so quickly. So like when this when people do begin to like kind of like discover, you know, this regenerative algorithm, or really, and when the ball of you know, creating this true AI, you know, starts to get rolling, that's going to roll extremely quickly. And you know, it's probably going to be pretty important for, you know, people like you to you know, position yourself kind of in a way, be like, you know, to be ready for this to kind of happen, because it could happen extremely quickly.
Oh yeah, Matt. I mean, I think about it all the time. I think you know, that's why I divide my time with the political message and the religious message. I mean, I kind of lose some people here, because I know there's lots of some technologists in the audience, and they kind of are turned off by the political and religious stuff. It really goes hand in hand, really. So I think yes, I really am anticipating that things will move very quickly at some point. So, do you know, I mean, I don't know if you heard the talk 2 weeks ago. Did you listen to that?
Oh, yes, I did.
Well, I mean, you know, I talked about you know, this idea of a destiny wave function, and basically, if you do something and the universe needs you to do it, then it conspires to make it happen. Okay. Now, okay, AI will be created, and true artificial intelligence will come, but anyone can do it. And there'll be lots of, you know, like it's been speculated. Lots of people have speculated that AI will come from nowhere. So I mean, you know, this idea of a lone hacker scenario, I mean, it's been speculated by loads of people. People like Eugen Schmidober speculated it might come from nowhere. People like Pedro Domingos, the master algorithm guy, has speculated it might come from nowhere. So all these kind of people, so there might be loads of people like me working on their own who are almost there. You know what I'm saying? You know, unknown. Even John McCarthy said, you know, some guy has already figured it out, but hasn't told us yet. You know what I'm saying? But what I believe is that, okay, a lot of people might create AI in the same way a lot of different people might win the lottery ticket. But what I think needs to happen is that okay, AI will never be created. But what I think inevitably needs to happen, that the universe needs to happen, is the revelation of the stuff we talked about 2 weeks ago. So I think the universe doesn't specifically care about whether I create AI or that person creates AI, that big person becomes next to Elon Musk or that whatever. Mm-hmm. But what I think is the universe needs the apocalypse, the unveiling of the hidden thing, to emerge. And I think if, you know, if my will is aligned to that goal, then the universe will conspire to realize my goal of creating AI if it's merely a stepping stone to do that bigger goal. So that's what I think. Okay. Now, something crazy happened earlier this year. For years, I've been quoting William Blake for the past 4 years now. And I've been saying the quote from Jerusalem, the long version, not the short hymn. He said, you know, the fields from Islington to Marylebone, Primrose Hill to St. John's Wood were builded over with pillars of gold, and there Jerusalem's pillars stood. So I've been using that quote actually since 2013. I've been using it at the end of the talks, not all the talks, but many of the talks. So the crazy thing that happened is that basically I was living in North London and I had to move out. It's lockdown, it's January, because some really noisy neighbors moved in and they had like kids. One was 2 and one was a baby. I can't feel bad because I've got small kids myself. But I was living on the ground floor and I had my previous partner, previous relationship, I had 2 small kids growing up in that flat. But before the people living in that flat above were basically 2 ex-Andrew Cohen cult leader followers, and they were like quiet as mice. It was amazing, great flat to live in. But anyway, this family moved and it was deadly noisy. It was crazy. And it was lockdown. It was insane. But luckily I was on my own, so I could move from room to room and avoid the noise. But anyway, to cut a long story short, I basically told the landlord, look, guy, I'm not going to renew my tenancy because, you know, too noisy. I've been with you 10 years. Now the guy's really good you know, landlord. He's a nice guy. He's a religious guy. You know, when I deal with religious people, I kind of know where they're coming from. You know, not a kind of falsely religious person. Anyway, I have a good feeling with this guy. And anyway, he had another property, and he said, "Wait, why don't you move this property?" And where's the property? Where is it? If you draw, okay, I won't take the exact address, but I mean, if you take the poem, you know, the fields from Islington, Marylebone, Primrose Hill, St. John's Wood, if you draw a shape, then the property is almost smack bang in the middle of that triangle. Okay. So to my, you know, you probably listen to my talks, you probably know I live in the kind of mythic, prophetic imagination. So most people would say, well, so what? It's a coincidence. Well, to me, that's like basically the hand of the universe, the hand of providence, giving me a sign. And the fact that DeepMind, you know, the new Facebook headquarters, the new massive Google headquarters, is also smack bang in that part of town. It's basically in that triangle. And it's not actually that big an area. You look on Google Maps, you know, St. John's Wood, Primrose Hill are quite close together. Islington's over here. And then Marylebone's here. It's like a thin sliver. You have Regent's Park. It's actually a tiny percent of London. It's actually quite a small area, you see. But I think that the creation of true AI will happen right there because DeepMind is there. And you know, one of the cafes I work in is actually a stone's throw from the first headquarters of DeepMind in Bloomsbury. So these things to me are not coincidences, you know what I'm saying? So I think the universe is steering me to create true artificial intelligence. I know it sounds wacky, I know, but I think it's almost as if, you know, I believe in this destiny wave function and I've kind of pursued this kind of crazy path on my own. And it's almost as if the universe is putting the pieces of the jigsaw puzzle in my path. So I know what you heard tonight is a bit rough and, you know, it's not 100% shiny. It is still a rough diamond. But I see the pieces of the jigsaw puzzle, you see, they make sense. And I think even at this stage, it's light years ahead of what's going on in DeepMind, in Google, in all these separate open AI, all these labs. So I think basically, yes, it will happen very quickly. And basically, at some point, it will just explode. But I think the universe is basically getting me ready. And I think at the same time, I'm getting myself ready for that time. It might be, you know, it might happen next year, 2 years' time, whatever. It happens when it happens. But I think it'll happen soon. I don't think there's much time with what's happening with the climate thing, the global warming thing, you know, wars and rumors of wars, maybe a great big war with China, America in the future. Who knows, you know? You know, on the borders of Ukraine now, there's also World War III could be imminent. You know what I'm saying? There isn't that much time. So I think it will happen very quickly. And I think it will happen at some point. And basically, yeah, I think basically the thing now is to get ready for it and get the code ready, get the basic, you know, to get the basic algorithm to back up all the stuff we've been talking about tonight. So yeah, I mean, does it answer your observation? Does it really, or you know, kind of
No, yes.
I know. I mean, basically, the talk from 2 weeks ago and this talk, they're actually one talk. I know it sounds crazy, you know, religion, science, you know, the hidden mysteries of religion, corpus hermeticum, the ancient mysteries of ancient Egypt, and then basically AI, machine learning and stuff. But it's actually one unified message.
Yeah, and that's what's so great about you. Way you don't like go too far down like one path. You're not just like a pure AI guy or the pure mystic person. You take parts of basically from the political stuff, the the AI stuff, the brain stuff, and it all like just goes together, and it creates a real balanced I don't know way of looking at stuff, and and it's important that all that stuff goes together.
Oh, well, thanks. I mean, Matt, I mean, my delivery, I mean, the ideas, everything is a bit rough and ready. But what I'm saying is, I mean, the Fractal Brain Theory book and the Quest book are full of typos and stuff. It's all a bit rough and a bit shoddy, really. But I recognize that. But what I'm seeing is basically the actual ideas themselves. I don't think they're just, I think they're basically right. And I think basically they're coming together in my head, but it's not me doing the work. It's almost like the universe it's taken this, not particularly genius guy, but he's taken this obsessive, pretty hard working guy, kind of like workaholic guy. And the universe has basically put the pieces of the jigsaw puzzle in my path to put together. And any mistakes are really purely my own. And I see basically what I'm doing is basically, it's not just, I'm a fanatic, and basically it's my obsession. But in my rational mind, not my intuitive, mystical, prophetic mind, but in my purely rational mind, I think to myself, my God, this is right. And I see what's going on in the world of artificial intelligence, machine learning. I think, my God, this is completely not right. So I see.
That's what's also so important is like your pursuit of truth. You don't seem to have like a certain agenda towards something like maybe some another person might have.
I mean, I'm quite frank in the Quest book. When I was a teenager, my early 20s, I wanted to be the next Steve Jobs. I wanted to be, Eldon Tyrell in the Blade Runner movie. I wanted to be like Elon Musk, this kind of. But I went through this journey, and things changed. So the journey changed. But yeah, I mean, there it is. I think basically. The world is looking for these answers, and I think I am putting myself in a position to gather these answers together and then put them in a format to present to the world. So I really, in the next months to come, years to come, I really need to get my act together and just get it out there, really, because I think I think loads of people think they're going to change the world and save the planet, but you just have to come up with a plan that makes sense. And then you have to basically a worldview, a Weltanschauung, then you have to communicate it. And that's the time-tested way of doing things. And I think that's someone has to do it. I think that you know what I mean. Anyway, any other question? Okay, any other questions? I mean, that's we've gone way out there, haven't we? Kind of really you thought this is a talk about artificial intelligence, machine learning. Yeah, go for it.
Do you subscribe to some in some form what Rupert Sheldrake and the likes state the kind of quantum field of thinking, like people thinking the same things, like the many innovations have come the same day, different parts of the world.
Yeah. I mean, Rupert Sheldrake used to talk at least once a year in the church I worked in for 10 years. It was a major New Age center. I mean, Rupert Sheldrake and his wife, it was Julie Purcell. I can't remember her name. Anyway, but yeah, I know his ideas, and I think the idea of morphic resonance fields probably converges quite well with this idea of destiny wave functions. The fact that there is a kind of reverse backwards in time causality means that if something is coming from the future back in time, then that's another way of synchronizing what's happening as we go forwards in time. So maybe the explanation he gives is not necessarily, corresponding to this destiny wave function. He might produce like certain bits of evidence, like, like the dog barks before you come home, therefore the dog kind of knew you were coming home. But there's other easy ways to explain that. So I think, the idea that basically inventions will come at the same time, if it is the case that there is a destiny wave function, there is a kind of like, a inverse kind of backwards in time causality, then that's another way of explaining. It's almost as if the object at end of time breaks up and sends shards back in time, and that these shards will be kind of rediscovered at the same time because it's, just came from the future. So I guess I'm speculating. I mean, there's different ways of looking at it. But I think lots of the new age, I think, are kind of on the same track, even if they do it in different ways, explain it in different ideas, and using different metaphors and different concepts. So I think, I think at the end of the day, I mean, I've been critical of the new age. A lot of it is money making. A lot of it is to do with getting people to buy your book and attend your workshop. But I think a lot of it is genuine. I think, I don't agree with everything Rupert Sheldrake says, but I think we're probably on the same wavelength on a lot of things. Yeah.
One more concrete thing about locality and non-locality. I don't know really if well you can think of kind of morphogenetic fields or kind of quantum field of thinking as having non-local and or local functions. And coming to the tiny part of London, if the kind of let's just take quantum field of thinking does have also local qualities, then those people coming together might have, even if you're not directly communicating, but you are still in the same cafeteria, same neighborhood, that might, if that would be the case, then the kind of the field consciousness might concentrate if it has local qualities, perhaps.
I think there's loads of things, like the idea of a destiny wave function would have seemed really like far out. I think there's loads of things waiting to be discovered. I don't really discount a lot of things really. So I think, the idea, a lot of things, I mean, just the destiny wave function is is almost like Platonic. It's almost like Hegel's idea, coming back into vogue, the idea that these other effects, synchronizing effects, which, the idea of synchronicity in terms of events happening, like this flat coming up and on smack bang in the middle of the fields of Islington, Marylebone, and Primrose Hill. I mean, that is like a synchronicity in terms of location, geographic location. And these are things which basically they can't be done by human agency. So I think there's something about the story of reality that involves these kind of like really kind of like almost like higher order scripts that are beyond anything that the humans can imagine. You know what I'm saying? I think there's a order. There's also as if like at any point in the Mandelbrot set is going to seem messy, but it's only when you have an overview you see this kind of order. So I think there's things happening in reality that manifest as things like synchronicities. And it's also that's too much that can't have been coincidence. That is something, the hand of providence showing her hand. It's almost like the destiny wave function has loaded the dice. And it's almost the dice was too obviously loaded. You know what I'm saying? Okay. So I think there are all these effects which then manifest, and they all work together to produce this set outcome, which has to be the case. And what we talked about 2 weeks ago about the manifestation of real magic is when I think the script of providence. I think the God as this kind of transcendent God, the Logos, as kind of order of the universe. This order of the universe is also like the greatest poet. You know what I'm saying? It's like the ultimate plot line. Yeah, and I think there's a kind of like majesty. There's a plot line that the people say truth is always stranger than fiction. That no Hollywood scriptwriter can actually weave a plot so intricate. Do you know what I'm saying? Yeah, and that will involve things like convergent. It's almost as if like a miracle. Like people people's minds merged into one kind of consciousness. It seemed you can give it different interpretations, but I think there's always kind of mysterious effects that basically shape physical reality, in mysterious ways. I sound like a Bible basher, I don't know. But I think, yeah, there's a hand of providence, and basically it will sculpt reality. The destiny wave function will sculpt reality in really interesting ways that transcend kind of reductionist science. And a lot of these are still waiting to be discovered, probably, all these effects. Okay, that does answer your question, Jury.
And way more.
All right. The great thing about Philip K. Dick, I mean, back to Varlas last talk, is basically that he really went into these questions in his stories. So I didn't realize that, but like the three stigmata of Palmer Eldritch is basically saying, basically at the end of the book is basically Palmer Eldritch revealing that everyone's God. That's what he's saying, isn't it?
Yeah.
He's the Christ character. It's like everyone's the Christ.
Philip K. Dick, in his talk 1977, propagating of the matrix and simulation. It was in one science fiction conference. Oh,
right.
You can find it from YouTube.
he was way ahead of his time, and basically he really things we talking about really he put in his sci-fi novels, I believe. And I'm amazed that in his Lawrence Sutton's Divine Invasions, his biography, it doesn't mention LSD. It's almost like he had the LSD brain without taking LSD, but by taking purely amphetamines. Amazing, yeah. Incredible. Any other questions? Marathon session again, absolutely marathon session. Amazingly patient audience, amazing. Any other questions?
Well, possibly
David,
relating to the destiny wave function. When COVID kicked in, I put a question out to the universe saying, I want to understand things at a deeper level. I want to use this time to go deeper, right?
Yeah.
And I just sort of fed that into the fed it into the keyboard and hit return, and wanted to see what would come up. And quite soon afterwards, there's a physicist who studies consciousness, who you will have heard of and possibly seen, John Hagelin. At Maharishi International University in Iowa. He did a seminar on, and there is a relationship here, on dark matter.
Okay.
And one of his own theories had predicted the emergence of the existence of dark matter.
Right.
His flipped SU5 superstring model, which of course I don't understand, but I get the pitch. And recently, some co-workers, and dark matter doesn't interact much with regular matter, gravitationally, right?
Yeah.
But recently, some of his co-workers had figured out that it decomposes fairly quickly in a couple of million years or so.
Okay.
Into another particle that has got a charge, maybe 1,000th the charge of an electron. Right. And because these particles are slow moving, he is saying they can be superconducting. This can be a coherent field, and would act like cling film. It would be attracted to the charged nervous system, right?
Oh, all right.
So I was talking about, actually, this gives a model for the existence of subtle matter.
Oh, right.
And a subtle body that, that carries on when you drop the physical body and so on. But that then gives you a mechanism for, I can imagine this somehow interacting with your work, especially because what's happening with dark matter may not be limited to 4 dimensions, right? So this is a kind of a gross printout, and there can be subtler stuff going on where you've got a super coherent nervous system that is maybe, John's saying that nervous system could be mind, and its interaction with the physical nervous system is what's going on in the brain, and so on.
What's really interesting is that we haven't talked about it much, is the idea, okay, if there is a, okay, you know, the counterclock phase, okay, that basically we are bouncing back to the origin. So, so you know, the CPT symmetry thing is that the time inversion, the big bang, the inversion is that there's a flip. So basically matter is antimatter, and matter becomes, antimatter becomes matter. So it's like figure and ground in the original emanation phase, which has given rise to this universe, going backwards. Okay, that is like say ground. Okay, so and then as we bounce back, then it's figure. That which is dark and unperceivable to us could be that kind of ground aspects. Okay, the kind of emanation aspect. Now, what's interesting to me is that the emanations which give rise to the universe. How does emanations influence the mind of an individual? I'm essentially interested in how, okay, this is bordering on the kind of like, I guess, more speculative. How do we get visions? How does a prophet see into the future? Why does, do you know what I'm saying? So I'm saying there's something about if the individual is basically a manifestation of the one God. Yeah. What's really interesting is if there's this kind of like the cosmic Christ at the end of time forms reality through a process of dissolution backwards in time, the ground aspect, and then the Big Bang we're going forwards. What is that kind of you know, universal vision at the end of time? What is it sending to certain individual minds as we go forwards in time?
As soon as you say what happens to the individual, I'm thinking, well, the individual is becoming more and more universal. This is basically sucking up more and more of an expanded unified field.
And getting more information. So,
yeah.
I mean, like Hegel saying, you know, basically, you know, the meaning of the word genius, is what we said in the last talk, is not some clever guy, you know, straight A's and went to a prestigious university. The idea of genius is like a shaman. The genius just receives from the higher mind. But then what is it? I think basically that the end of time is the state of all knowledge. But in order for the going forwards in phase point to basically reconstruct the universal vision at end of time, the universal vision at end of time sends back these kind of like, you know, chunks of knowledge to certain individuals for the progression of history. And these are your geniuses. These are, as Blake understood it, you know, your poetic genius and your prophet is of the same kind, is from the same source. So, I mean, back to what you're saying about this membrane, that somehow, you know, we can influence our physical bodies, but also our brains. And then I think this kind of dark energy or dark matter or whatever is kind of like the remnants of that initial counterclock transmission phase. And it's almost like, okay, the universal vision is not there anymore. We're basically bouncing back to it. But in its dissolution phase, it's basically sent back the means for it to be reconstructed. And along the way, it's not like, you know, it's all or nothing. We basically create the universal vision or nothing. It's that along the way, there's these kind of like intermediate points where we kind of recreate a kind of mini, you know, cosmic Vishnu on the planet, on a planetary scale. And I think one of those critical junctures is now. I mean, years ago, when I was heavily involved in the psychedelic scene, years ago in my 20s, people had all these visions and stuff, and, you know, back to Philip K. Dick again. And they weren't wrong. They basically, you had all these kind of like, you know, messiahs and kind of like King Arthurs, and they all thought they were the chosen one and stuff. They all had these visions, and Terence McKenna's and stuff, you know, lots of Terence McKenna's I'd meet. And they all had the same visions, basically, I find. And they weren't wrong. They just basically didn't have the facility to take these transmissions that they were getting, which I think were genuine, but it just didn't have the means to kind of apply them. So I think these, you know, fragments are transmitted back to lots of different people. But I think maybe it's in it some critical junctures, and some critical people will actually manage to finally manifest, you know, the get all the pieces together at the end.
Maybe we all get there. I put a link to John Hageling's webinar in the chat.
Oh, okay. So any other questions? I mean, that's a wide-ranging talk. So anyway, what will? Any other question?
Yeah.
Oh, okay, Jerry.
some small continuation on that. And wouldn't it be kind of more elegant way of thinking that instead of someone or something or some structure kind of beaming, concentrating these patterns to certain people, like other than that, more like the wave coming to everyone, but it's then a question of the human mind, the human brain, as like a telescope that can be more or less sensitive and directed and calibrated into a certain wavelengths, aspects, patterns. So
Jerry, I know exactly what you're saying. Years ago, I kind of had this idea that there's a kind of like, there was an overground means of getting these revelations, which was perfectly rational. And there was an underground kind of mysterious way of getting it. And so I'd arrive at these ideas, and basically it's because I read certain books. Basically, that's overground. I can see I've read this book, I read that book. It might be this is my 20 years ago. I don't do it. I have a dose of LSD or Charis, and then all these ideas became fused into a realization. But that's completely overground. See, I can see I've read that book, read this book, read that book. There's nothing mysterious about it. Okay. But then I saw that there was a mysterious dimension, that these books and this knowledge was actually coordinated to receive it anyway. But then there's the other kind of like transcendent that isn't to do with anything I can, kind of like log and rationally, list that this happened. This is the really mysterious dimension. And I think basically there is this kind of transmission to people in certain times, and these times will be times of chaos and times of transition when the old order breaks down. And I think then the mind becomes much more receptive to these kind of visions, I suppose. Like winter solstice. Now, years ago, a kind of like young, quite attractive hippie chick said to me, this was when I was quite skeptical about mystical things. Actually, she said, "Your winter solstice, the veil is thin." Okay, I thought it was nonsense. But then over the years, I discovered really winter solstice was this really powerful time when the veil really is thin. Can really no drugs or whatever. I used to wander around Hampstead Heath and like the American Indians smoke cigarettes, and that really tipped me over. Wander around Hampstead Heath and then basically meditate in the dark and then just basically concentrate. And I can really get in these quite mystical states. But I think in times of chaos, in times of transition, like the world is heading into now, with ecological catastrophe, with maybe another virus or whatever, another real kind of free scenario, then I think people's heads become very, very, the veil becomes very thin. And I think then the transmission really does happen. And then people without drugs, without any meditation, without anything, they will see visions, they will dream dreams. I think basically then it's almost as if the destiny wave function then really inserts itself. And then it was as if things happen very, very quickly. And then you have this phase shift. Now, on one level, it sounds like miraculous and, kind of like really strange. But on a higher level, when you think in terms of destiny wave functions and stuff, it's just this pure, there is also a purely rational explanation to it. So I think, back to what I was saying, there is this overground thing of saying, oh yeah, so these people are stressed, basically there's wars going on. Basically, young people stressed about global warming, about chaos, about, COVID restrictions and stuff. And it's causing people tipping over the edge. It's making them schizophrenic. Therefore, they're having these funny, insane thoughts. That's the overground path. But the mysterious path is that then what they're seeing is a kind of like, do you know what I'm saying? It is from a higher mind. And that is a leap of faith, I know, because I didn't believe it in the past. But then we start having these visions, and oh yeah, that's the mysterious underground path. But the two overground and the underground interact into.
Am I able to? Am I here now?
Yes.
Yeah. Can you hear?
Yeah. Who's that? Who's that?
Roland Orre. In there. So.
Okay,
I had obviously my audio settings were not for the microphone was not so good, so I was not hearable earlier. So, but when you mentioned this thing about dreams and things, I recall when I was pre-15 years old, I very often dreamed completely true dreams, which appeared within this reality a few days later. At that time, at that young age, long time ago, I was thinking I just had seen this future. I mean, I had read a lot of Hawkins and Einstein's theories and such, but no. So sorry, silent, please. But later, I understood that what I likely saw was not the future, but the past.
Oh, right.
So earlier instigations of what I consider a weird computer game. So my main theory, which has been since 1987, when I had a kind of revelation, you can say, is that this reality is some kind of weird computer game, which is, well, 37% now on my plausibility list of what this reality is. But I think we have been here before, and we have been stupid enough to play this game more than once. So that's what was my comment.
Oh, okay. This is I've never spoken about.
Sorry, in my life. It is 11.
This is interesting, wacky talk that. Yeah, Roland Orr. Anyway, yes, years ago I had a dream, and years ago when I was 12, and it was crazy, and it's crazy. I basically dreamed something which totally didn't correspond with my reality or what was expected of me, and that dream totally came true later on in my life. I actually wrote the dream down. Actually, it's in my mother's house. It's in a book of dream journal. Now, when I was 12, there's no way I would have believed that dream would be my future. Okay, it was kind of, it involved mushrooms, it involved me being unemployed, it involved me drifting in a strange underworld. Okay, because I was a straight A student. I was good at everything. You know what I'm saying? I was in 1979 when unemployment was really high in the UK, and basically I was 9 years old. I was voted the guy in class most likely to get a job. So I really was, the guy who was going to succeed in life. Anyway, this dream was really like a journey into the underworld. Okay, and then basically I wrote it all down, and it actually unfolded in reality. It described my descent into the psychedelic world. It described my journey, wandering, in kind of London's underworld and stuff, and having these funny experiences. But there's no way that I could have guessed that would be my fate in the future. You know what I'm saying? But it completely predicted my future, and it was a very long dream. It was very detailed. And then, even when people tell me they dream like Jung and stuff, and it gives you like Joseph Campbell, my rational mind doesn't really understand it. I mean, I speculate that maybe, some kind of destiny wave function can influence, but what's happening in my brain. But this thing, this dream I had 12 years ago that I wrote down is so uncanny. You think, there's no way that I could have imagined it. You know what I'm saying? So I'm not saying I'm saying I'm open-minded to these kind of things. I really am. And I think in the sense of us living in a computer simulation completely, that's what the last talk from 2 weeks ago, that's exactly what we're talking about. That the universe exists as a mathematical object, that basically we're all one consciousness, and that we're living in basically the idea of simulation theory, that ultimately the mystical experiences that we are the simulator. That simulation theory, which is very popular in Silicon Valley, is essentially mysticism for nerds. But the crucial idea is that basically is to understand where it merges with religion, is to realize that you are the simulator, and that ultimately you are it's not turtles all the way down. You are the turtle. That's the that is real. Simulation theory converges with the core idea in religion, I suppose.
I have a further question. What your opinion?
Yeah.
About consciousness?
Oh, yeah. I mean.
No. I'm not ready with my question yet.
Okay.
So I did my PhD within computational neuroscience.
Yeah. Roland, I like your posts, by the way. You have.
Yeah, you have seen it. Yeah.
Yeah.
Okay. So, but my PhD opponent, Hava Sigelman, who is a expert in super Turing and hypercomputation, have proved that the brain is super Turing. But the question is super Turing sufficient for consciousness, or does it require hypercomputation? That is super Turing in the continuum limit.
I think basically, if I think some things are not computable, okay, from a computational standpoint. But I think if the answer is already existing in the future, you know what I'm saying? If the answer is already existing, you can't compute it. But basically, the answer can decompose itself back into the past, and then the computational processes of physical reality can then reconstruct that non-computable thing. Does that make sense? So basically, the answer is already seeded in the initial conditions of the universe, but not in the actual laws of the universe. So the universe runs in a computational way, and then it goes forwards in time, but then it regains the answer that is actually non-computable, because the answer was already seeded in reality for the computational process defined.
I can't say if it makes sense, because I'm just thinking about the computability, so to say. And you maybe have seen my motivation for the brain to be super Turing, which has also been approved by my PhD opponent. And it doesn't explain hypercomputation as such, but one can see where it leads to.
One thing we didn't talk about tonight, because it's beyond the scope of a quite introductory skimming stones talk, is what's central to my work is the idea of recursive self-modification. So I think there's an extended theory of computation where basically the way to explain it is basically, okay, the theory of computation involves Turing machines. Okay, you've got the tape and you've got the machine. Now, the idea of recursive self-modification, okay, which I believe is essential, and the actual Turing machine is like a limiting case of this wider theory, is where the actual tape itself is the machine. So by writing on the tape, you actually change the machine itself. Now, with respect to von Neumann architectures, I mean, von Neumann did something clever because he, unified the data store with the instruction store as one store. That's an innovation we take it for granted now. But there's a further unification, because what if it's the case that basically the operands, okay, and operators, data and instruction, are the same? Okay.
Yes, so, I mean, I completely agree upon that, because that's the whole idea with neural networks.
But then writing this kind of recursively self-modifying von Neumann machine is that by actually writing into the memory, because the actual, the operators, operands are one and the same, you actually change the actual the CPU of the von Neumann machine. Yep. So basically, it's recursively self-modifying, but actually writing into the memory is also the CPU itself. It's recursively self-modifying. Now, that's quite theoretical, isn't it? I mean, Stephen Wolfram's, cellular automata, I think he's missed a whole class of cellular automata. He's got, class 1, 2, 3, 4. He's missed the class of cellular automata whereby the phase space that the cellular automata creates is an extension to the actual mapping set of the cellular automata. So it's recursively self-modifying again. Now, I know what you're thinking. You're thinking crazy combinatorial explosion. But I think the way to do it is what we talked about earlier, this differentiate, select, amplify, algorithm. The thing is, I mean, we think that the critical generative algorithm in AI involves evolution. But evolution itself is inherently recursively self-modifying. It's a very old idea that evolution evolves evolvability. Do you know what I'm saying? So basically,
yeah, absolutely.
the units of evolution become the future building blocks of future evolution. So I think this is one of the things which is captured by by my work, which is basically an inherent part of the theory, which I couldn't go into tonight. So I think there is an extended kind of like computational theory, which is purely recursively self-modifying, and the existing theories of computation are like subsets, like limiting cases of this kind of extended theory.
Yeah, I mean, I completely agree. I mean, I'm not an expert in super Turing or hypercomputation, but my PhD opponent have actually proved that a super Turing machine, like a recurrent neural network, can emulate any Turing machine.
Well, yeah. It even by going into the generative. I mean, Gregory Chaitin talks about in his book Metamaths. He's very interesting because he's talking about in the final chapters. Okay, he's talking about formal axiomatic systems. That's his work, isn't it? Does a lot of work with Gödel. Okay, in the final chapter, he speculates. Okay, he asks, is there a dynamic formal axiomatic system that can generate all the other formal axiomatic systems?
Yeah,
we think the answer is yes. We think it ties in with another question. What is the simplest, most simple formal axiomatic system there can possibly be? We think it involves starting at the bit level, because the simplest symbol involves one bit. We think the simplest kind of inference mappings starts at a bit level, binary trees. And we think the dynamic formal axiomatic system he's speculating about is not just about generating kind of like from a fixed symbol set and a fixed set of inference rules, is that the dynamic formal axiomatic system generates the inference rules as it goes on. It's recursively self-modifying, do you see? And it bypasses Gödel, because Gödel's incompleteness theorem about, basically if there's some unprovable proposition, he's saying basically that you bypass it by adding that unprovable proposition as one of the initial axioms. But if your actual, saying your system is not a system of logic, it's basically the system which generates systems of logic. You even bypass Gödel's incompleteness theorem.
Yeah.
Awesome.
Okay.
Great. Yeah, this is this is computer science. This is like really interesting questions in computer science, isn't it? Really.
Yeah, absolutely.
Far out. That's really. Any other questions? Any other?
I'd like to get one more question in. What would you say to transhumanists who believe the purpose of AI is to give rise to these machines that will become the next dominant life form on planet Earth, and that we'll eventually upload our brains to these machines for kind of a digital immortality?
Well, my simple answer is, Matt, I think it's completely misguided. Completely. The whole, the humanity plus transhumanist movement, I think it's completely grounded really on the wrong assumptions. I think basically the original humanism from the Renaissance was really grounded on, religious assumptions. And I think when you lose that kind of I guess the true mystical aspect to what humanism was about, then you have something really kind of not watered down. You have something basically which doesn't make sense. And I think this idea that, we have these always kind of new religions emerging, like, Yuval Noah Harari writes about datism, Dan Brown writes about the internet becoming the new God, what I'm saying? I think they totally missed the point where, if you can reestablish the true humanism, then I think basically all this Natasha Vita-Moore being so terrified of death, needing life extension and stuff, and really pursuing this life extension thing, it's a very materialistic humanism. I'm not saying it's bad. I'm saying, that in the last talk, we talked about technology being, total power, total knowledge as being something divine, as being something, gifted to us to explore science in order to create technology. But it was not for selfish ends. And I think you can have it alleviating human suffering. You can have life extension. You can give yourself 1,000 years, 1 billion years. But unless you have that kind of transcendent, peace of mind, you know what I'm saying? It's kind of foundation of what humanism was about. Then I think all these kind of materialist, kind of scientific, transhumanist ideas are really kind of misguided. They're never going to find their kind of source of and the goal of kind of uploading your consciousness into a machine, I think it's just totally wrong. I think it's like almost like a, do you know what I'm saying? It's almost like putting yourself into a trap, like a hellhole. You know what I'm saying? I don't think a finite machine can contain consciousness which is infinite. I think basically there is, the consciousness conference I went to 2014. There was a kind of aversion towards the quantum side of things, because I think Roger Penrose and Stuart Hameroff get it wrong because they emphasize too much on the microtubules. So I think there is something about the quantum relationship to consciousness. And I think it has to do with the fact that the quantum state is not finite. Okay, and I think that basically consciousness in its infinite form doesn't correspond to any finite form, a localized point in space. And the idea of this transhumanist idea of putting your consciousness into this machine, I think it's death. I think it's basically they're believing they're achieving immortality in this machine. Yes, for sure, the machine will behave like your transhumanist, adherent. It's like Ray Kurzweil wanted to recreate his dad in a machine because he was so affected by his death early in his teenage years. Sure, you can create a simulacrum that's going to behave like your dad and say the same things like your dad, but the thing is going to be like a zombie. So I see these transhumanists basically really aiming to put themselves in this kind of zombie state, thinking it's some kind of immortality. That's what I think.
I have a comment on that.
Yeah, go for it.
Yeah, because I have always, I haven't always known about the Kurzweil being at all artificial I hype, as I would say, because I don't believe in it, so to say. I mean, when we create a machine who could be like a human, what does that guarantee that we have created the next step in evolution, so to say, to increase the evolutionary rate of this reality? So I realized quite some years ago that what we need for this is weak AI, not strong AI.
Yeah.
To collect all the ideas out there. And this is my business idea. We also have certainly seen about it, and I won't talk about it now, but basically to make all ideas open source, to make the evolution happen. That's basically what my idea is about.
Oh, no, completely. I think one of the main impediments to scientific progress is these kind of paywalls and barriers to knowledge, I think.
You think so?
Oh, no, completely. Elsevier and all these publishing companies are ripping off scientists, are really impeding the progress of science. I'll tell you a secret. I mean, even though I'm a maverick researcher, I have actually access to more literature and books than most research scientists, and I have it all in PDF formats, and it's all, you know what I'm saying. So I think there's a kind of funny, I'm gifted with all the kind of latest information, and it's in a better format than actually it being in a research library and actually having to ask librarians for big thick tomes. You know what I'm saying? So I think scientists work in this kind of constrained way with paywalls and limited access to information. And I think in some ways, being in my situation, I mentioned actually, I actually get access to information easier than a lot of people working in research institutes. And I'd have to, basically flick through magazines. I got it all in kind of more easy accessible format. So I think yes, one of the main impediments to progress and knowledge is, okay, not just these publications restricting the flow of information, it's also patents as well, I'd have to say. So I think in the future, if we can actually, make this kind of social transformation, great reset, revolution, system change happen, I think one of the things is to open source absolutely everything. No patents, you know what I'm saying? It's all free flow of information. It's all, everyone's on universal basic income. And I think that is the future. I think that is, if you want a good society, it has to be free. It has to be, information has to be free. People need to still work. That's for sure. But I think communication, freedom of consciousness, freedom of information are absolutely fundamentals. Yeah, absolutely.
On that point, obviously you're putting all this information out there, and we're not in that society yet.
No.
So are you worried that someone might steal this concept and run with it ahead of you, or because you want to form a business of some kind, right? So
really good question, Oliver. That's the reason why in these talks there is some level of self-censorship, because there's lots of ideas which are very, very patentable. And basically lots of people are driven basically by money, and a lot of people come to contact me with the AI stuff purely in order to, because they're interested in money, basically. I gave a talk at UCL, University College, London, for the Artificial Intelligence Society, purely because I gave a talk for Funzing, which is more kind of like, a general kind of promotions company doing talks in clubs and pubs. And some UCL students saw me and they said, we've got to have this guy on, basically. Okay, it was a storming talk. I mean, it really kind of like some of the people would have thought, why the hell have you got this guy on? But the people really they loved it. Okay, they loved it. Now, there's a whole throng of people came up to me at the end. They're all involved in startups and incubators and, kind of like venture capital companies. So there's a kind of hunger for AI, but a lot of it's to do with basically making money. And, so I'm very aware that basically what I'm doing is very, very, in demand. Over the years, there's been 2 offers separately to get funding from DARPA, which is the US Defense Department Research Agency. Lucky I didn't go down that path. But I've got to be careful, because I'm trying to basically angle what I'm doing as something far bigger, not just to create a startup at the end of time to become the next Microsoft or whatever, but as something far more. And also you attract better people if you have these kind of higher aims. I think people who just want to make money, they're going to let you down. They're just going to get involved and just smash and grab, basically. So yeah, Oliver, I'm very aware of this factor. Yeah. Okay, so any other questions? Okay, that was oh my God, that was 3 hours, 26 minutes. My God, it's really long. Anyways, I think, unless we have any other questions, I guess we'll end it there. Okay, thanks everyone for being so patient, and see you at the next talk, which will probably be at some point next month or early in the new year. Anyway, it's been great fun.
Yeah, it was fun. Thank you a lot.
Great to finally meet you. I've been seeing your name, and great to see you.
So same to you. I only seen you on the
fantastic. Loads more to come. I mean, there's loads more computer science stuff to come. So really, even though the work has been to do with fractal brains and genomes and stuff, there's basically a ton of information about computer science and formal axiomatic systems in my head, which I can't really give in talks because I can't get an audience to listen to them. So what you heard about Gödel and stuff just now in formal axiomatic systems and Gregory Chaitin and stuff, a lot of what goes on in my head with the coding of the algorithm is exactly in this space of recursively self-modifying algorithms and formal axiomatic systems. But obviously, you can't give a talk about that, can you? I mean, Russell North Whitehead and Bertrand Russell, they had to self-publish because there's not enough people interested in set theory reduction of all mathematics to actually to get a publisher to publish their work. So it's like, anyway, in the future there'll be loads more talk about algorithms and recursively self-modifying algorithms, etc. So anyway, fantastic. Anyway,
is this book familiar to you?
No, it's not, but it looks amazing. It's got the word logic in it.
I'll send it to you.
Who is it by?
Sorry?
Who's it by?
Who's the?
What is it about?
Well, it's about exactly about Alfred Whitehead and Russell and their endeavors. It's a graphic novel. I'll send you.
Ah.
Well, man, I mean, I might be able to. Well, Jiri, I mean, that's very good of you. That's very generous of you. Let me get back to you because I might have it already somewhere. Okay, so I might better get it somewhere. So I mean, it sounds amazing. But thanks. That's most generous of you. Alfred North Whitehead, absolute genius. Yeah, absolutely. But it's like that. Yeah, it's like that. So a lot of the work is basically so recondite and it really is esoteric. I mean, the talk 2 weeks ago was esoteric. It was esoteric religion. But a lot of the stuff in that goes on with the coding of the brain theory everything you heard tonight is basically stuff which is made to be as accessible as possible. But some of the stuff to do with the coding of the thing, one, it's patentable. It's very, kind of like a very, is technology basically, but it's very kind of like formal. And in the future, when I can get more of an audience, then I probably will give lectures about the kind of really abstract stuff. So that's in the future. Anyway, great. Unless anyone has any.
I have been having a lot of thoughts on cellular automata the last few months. Ideas of expanding it to so many multiple ways, and I'm kind of getting the idea that I have to do something with these ideas. I don't know if they are going to connect with your work. Probably from some places.
Oh no, completely. I mean, what we talked about earlier. I mean, string substitution systems. I mean, cellular automata. What they are is essentially string substitutions on a spatial grid. That's what they are.
Yes. Yeah.
You know what I'm saying? It's spatialized string substitution, which is exactly what we've been talking about tonight. It's basically spatialized cellular automata.
Yeah. Well, that was a new angle for me to cellular automata. So it's really.
Oh, fantastic! No, this is completely. And back to your first question, we're talking about essentially cellular automata, spatialized. With this scaling, shifting, continuous factor involved. So yes, it's gritty and discrete, but it also has this continuous aspect as well. So I think at the end of the day, I mean, basically, the fractal brain theory decomposes to really like that which is basically it's that which generates the grid, but it can generate the grids recursively to infinite size, like we talk about the polar frontal cortex. So cellular automata has a grid, but the grids that the brain can generate can infinitely recursively nest. So with this polar frontal cortex ability, do you see? I can have a grid, but I can recursively nest grids within grids.
Yes, yeah.
And that grid can represent an entire city. I can, the grid can be, I'm in this street, I turn left, I turn right, it opens up to more grids. I go into a house, that's a grid. I go into that room, that's a grid. I see a painting, I go into that painting, I listen to music. So basically it is like a cellular automata where the grid just grows and grows and grows. It's basically Kenneth O. Stanley's open-endedness. You create the field of action, but then the algorithm also generates the agents and the interaction between the agents. It also generates the recursive self-modification of those agents. It also generates the recursive interaction of those agents. Do you know what I'm saying? So it is Kenneth O. Stanley's open-endedness, and it's basically recursive self-modification implemented into automata to infinite size.
I think what you just said can be described by lazy evaluation, if you are familiar with that computational science concept. I mean, because all that information can certainly not be coded everywhere at once. So when your consciousness investigate that, it evaluates more and more to more and more detail.
Well, yeah. I mean, it's like your differentiate, select, amplify algorithm. I mean, quantum computers. I mean, basically, you have this. They can search all the superpositioned possibilities at once. Okay. If there's a destiny wave function which basically biases these quantum claps of the wave function, then effectively the future can then bias the calculation of the quantum computer that's the entire universe. So yeah, I mean basically I think in artificial intelligence, machine learning, you have these ideas like what's called Solomonoff induction, and basically you have this thing called AXE that needs a kind of infinite amount of computing power to work. Okay, that's all very well, but it's not very practical, is it? I think it's like but what you can do is what we can do is basically, we talked about algorithmics earlier a little bit. I mean, I skipped over it because of lack of time. But what's missing in basically the theoretical AGI world is basically the generator of these generators. So this is back to what we talked about earlier. The theory is it's to do with this thing called algorithmic compression. Okay, so basically it's work of, it was back to Gregory Chaitin, but also people like Kolmogorov and Solomonoff induction. It's basically the idea that basically intelligence is decompression, and basically when you produce a whole bunch of behavior, you have a decompression device, basically decompressing all this output, all this. The trick though is to find those compressions. Therefore, learning is the actual compressions, but what they're lacking, okay, barring the having this infinitely powered computer, which doesn't exist, is the means to actually find those compressions. And I think the means to find those compressions is through evolution. And I think that is the master algorithm, and it works through differentiate, select, amplify in a recursively self-modifying way. So no, we can't, like a quantum computer super position search every single possibility. But what we can do is basically we can differentiate, select, amplify, and concentrate our kind of resources into a small subset, and then recursively search that subset. And I think that's what really evolution is doing. And with the biasing of the quantum probabilities from this destiny wave function, I think it's kind of guiding the answer back to the cosmic Christ, the set conclusion. This non-computable thing, this non-computable value, which is, you can't compute it, but it's already been seeded in the actual initial conditions of the universe, so it bounces back to it. Okay, that's a bit abstract, wasn't it? Wow, that's marathon session. Wow, that's this is we can go on for hours. But Matt, I read your mail. I will do like Q&A sessions,
Oh, yeah, that sounds good.
So
that'd be a good idea. Good idea.
Matt's just doing Q&A sessions for Patreon donators. But I thought anyone who donates, or anyone who's really interested, basically to just do Q&A sessions at least once a month, and then in future maybe once a week.
Yeah, well, you can see just how crazy, and just how main directions, just like the Q&A at the end of these talks, how many directions they kind of go, and your talent of really taking a question and really running with it, and being able to get a lot out of it.
But yeah, I mean that's the great thing, is that in tonight's Q&A, stuff came out about Gödel machines and all this kind of stuff that would just not be in the main body of a main talk, because it's just too. But it is really interesting. Okay, so any other questions, or else we'll wrap it up. Epic evening.
I do, but I think I'm going to save it for another time.
That's an incredible 3.5 hour session. My God, it's going to take ages to upload to YouTube. but anyway, I mean, excellent. I mean, thanks for being so patient. I mean, these talks really help me, because they help to get the ideas together. So obviously over the years, I'm just going to hone and refine, and basically chop up into bite-sized pieces, and then you just get it out there. So thanks for being so patient, and thanks for listening. Any other questions, or else we end it there? Great, thanks a lot. Thanks everybody for attending, and keep in touch, and link up with me on social media, support me on Patreon, donate, join me, whatever programming, whatever, get in touch, and we'll hopefully see you again. Okay, great, fantastic. We'll wrap it up there. Great, thanks a lot. Thank you very much. Thank you very much. So excellent. We'll guess we're going to stop record now. Stop the recording, and we end it there. Actually, I'll just stop the recording, and then stop the recording, and let's just keep it live. Stop recording.